Okay, I'm sorry. Good evening. This is helpful for CBSE. Good evening. I audible, beta? Am I audible? We can't able to hear you. Okay, my bad, my bad, my bad. This mic was switched off, so my bad. I hope I'm clearly visible and audible, everybody. Everybody can hear me now, guys. Hello, 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 hello. Now everybody can hear me, please. Okay, okay, okay. So Tarun Kumar Tarun Kumar, good evening, beta. Mahesh, good evening. Keshav, good evening. Then we have Lata, good evening. I hope I'm clearly audible and visible to everybody here. Guys, guys, just give me a confirmation. Hello, hello, hello. Now, as I was saying, let me repeat that because that was my bad. The mic was switched off. Yes, this will help full for yes, beta. Keshav, definitely it will help for full class 12 syllabus, but yes, it will rather be more helpful because beta, if you're completing your class 12 syllabus properly, then your NCRT exercise is definitely more than sufficient for making a question for JEE Mains and rather JEE Advanced as well. But yes, you will be requiring more questions to practice. So Aditya Rai, Rudra Pratap Singh, good evening everybody. So this class is sufficient for your class 12 boards as well. And many of our Lakshya JEE in English students who have already enrolled, but because they have enrolled, I guess, uh, just 1 week back, so they also have missed the chapters of solution and obviously the electrochemistry part also. So this is a revision, a thorough one shot for them as well. And all the students who are willing to join us at Lakshya JEE in English, then you are also welcome. And even if not, I have no problems because we are here for your good. So wherever you are studying, it is our moral obligation to help each and every student out there. So with that intention, I am here. But beta, all those who have already joined Lakshya JEE in English or you are planning to join Lakshya JEE in English, then beta, please do these chapters with the recordings as well, because those recordings will give you the thorough analysis of all the topics that we break this one chapter into variety of lectures, and those variety of lectures will give you variety of questions, and that will help you to practice the topic and then the related question. Obviously, with the one shot, everything has to be made precise, concise, and that concise knowledge is only helpful once you are revising. But so I to have not, so that means I should not watch this. No, if you're starting from zero and if you have no access to those Lakshya JEE in English recordings, then definitely this session is more than sufficient for you for your class 12 bowls as well, and for your JEE Mains and JEE Advanced paper as well. But beta, you have to topping on the ice, topping on the cake, the icing will be your hard work, your practice questions, because the more you practice, the more you will be able to solve such questions. So shall we start? This batch is free. Beta, this is Keshav. This is just a revision, a backlog marathon revision session for all the topics that we have done in the Lakshya batch of our Lakshya JEE in English. So this is no free, obviously, these backlog sessions are absolutely free for you in YT, in YouTube. So I hope, Keshav, I replied, beta. Then Sanatan is asking, sir, can I start from here? I have backlog of 2 chapters. Yes, Sanatan, that is the reason we are here, beta. And beta, if you have not done anything, then there was a backlog series of part 1 of solution chapter. In that solution chapter, in that backlog series, I have discussed the first part of solution, sir, which is the concentration terms and the application of those concentration terms to solve those questions, because those questions are again valid for your boards also, for your mains also, for your advanced also. So what I'm going to do, start with this class, because the colligative properties were pending for solution in colligative properties. So our first task will be to complete those colligative properties. And then after completing those colligative properties, then we'll be focusing on electrochemistry. And what part of electrochemistry we will be discussing today, sir? Electrochemistry, we will be discussing the most important and crucial part. What is it, sir? About the electrochemical cell. About the electrochemical cell. That means a cell which spontaneously has a spontaneous chemical reaction and it gives you energy, sir. That means we are going to discuss about the batteries. Obviously, chemistry is in everyday life also, and most loved part by JEE Mains also, JEE Advanced also. So all those Nernst equations, concentration cells, I'll be discussing complete advanced topic. So don't worry. Yes, but electrolysis and those conductivity, those remaining two parts, that we will, because that I have not even discussed. We have done this much only in our Lakshya JEE batches for electrochemistry till today. Therefore, I'll be sticking to the part which is electrochemical cell and the questions of Nernst equation, thermodynamics around it. So I'll be discussing only till there, not apart from that, because obviously the time that we have today, let's say we will finish this part in initial 1 hour, 1.5 hours, and then we'll be requiring maybe 1 hour that colligative property will take, and then this will take around 1 hour or 1.5 hours. I'll just turn the slides, because this I have for solution and colligative property. Then we'll have a 5-10 minutes quick break, and then we'll be starting with electrochemistry. Okay, so cool, everybody's charged up, ready with pen and copy. Ha beta Keshav, I have been teaching since 2012. Yes, largely offline before. Sir, voice is too good and comfortable. Thank you, Sanatan, for the compliment regarding my voice. And I was communicating to Keshav. Keshav, I teach organic, inorganic, physical, each area of chemistry, because stop clarifying only. Acha, I'm sorry. I am not planning to offend Mr. Gamer. So Mr. Gamer asked me, stop clarifying. Okay, I have stopped beta. Will you? Yes, yes. So Mr. Gamer, you can obviously ask anything. Why you are scolding at me? I am not only reading his comments beta, I'm reading everybody's comment. So I take every area of chemistry since 2012. Rudra Pratap Singh, sir, I have completed physical chemistry 2. Okay, 2 chapter. Kinetics and solution, I can't attend. Kinetics and solution, can I attend this lecture? Beta, if you know solution, then the first part of my lecture will be for colligative properties, and the second part will be electrochemistry. So I hope I answered you. Sir, in YT as in YouTube. Sorry, sir. Nahin, gamer. No, sorry, beta. You are asking question and you deserve to be answered. Every student deserves to be answered. If a teacher is not replying to a student, then this is teacher's bad, because beta, a teacher does not exist. A teacher has a value 0 if he or she, so it is not able to help you people. Chalo. So shall we start the session, beta? Chalo. So first, as I've told you that half of the solution we have done. Yes, Mr. Pratap. Okay, so we are starting. So half of the solution and colligative property we have done in the previous live. So kindly, if you are new here, kindly after the class, you kindly go to previous live, and then you search, you learn the concentration terms, and the second part of solution and colligative property chapter is the colligative properties. Now, what is colligative property? All the properties which depend only upon the amount, all the properties which only depend upon the amount of solute with respect to solution are known as colligative properties. है ना? So, अच्छा, Keshav is asking, sir, organic chemistry will you take in YT? Beta. I am taking only those chapters right now. Why? What we mean by backlog series, that you are very much welcomed to join us at Lakshya JEE in English. And once you will come and join there, sir, the 2 chapters are already 1 chapter solution, and half, more than 60% of the 70% of the chapter of electrochemistry is done. So, sir, that's why we are here to give you a backlog marathon of all the topics that we have completed in our Lakshya JEE in English batch. So this is a backlog for you if you intend to join us. But yes, obviously, if you are not planning for that, then beta, obviously, as time will pass and as nature and the team will allow us, so we'll be coming up with backlog sessions of the complete syllabus. But yes, That depends upon the availability and time, beta, है ना? How can I join? Acha Keshav, you do not know how to join? Go to PWJ in English. I guess the link in this video link also, Lakshya JEE in English batch description is there. Just go to PW app, search Lakshya JEE in English. You will be seeing my photo along with Deepen sir's photo, along with Gokul sir's photo. Click into it, pay the nominal amount which is already discounted because of the 6-year anniversary celebration, and then enroll for the batch, and then start learning. Chalo. I hope, Keshav, I answered, beta. Chalo. Now, sir, what are colligative properties you were saying, sir? Colligative property is the property which depend only, which depends only on the amount of solute with respect to solvent. Sir, but this colligative property is valid for what type of solution? It is valid for only solid in liquid solutions, and it is only, colligative properties only have their significance once the solution is dilute. This all things we have discussed in the previous session. Now what new? Now, after discussing, we saw that whenever you dip a non-volatile solid solute in a volatile solvent, the vapor pressure of the solvent gets reduced, because now it is not a solvent, it is a solution having a non-volatile solid solute. So, sir, the solution, the pressure will decrease, yes, and the decrease in pressure with respect to the initial vapor pressure of the solvent is called relative lowering. Okay, so after that we have used Raoult's law and Dalton's law and formulated the formula for a solution. So if you mix two components, because JEE generally asks questions for two components, so if you mix two components and make a solution, then the vapor pressure of the solution is equal to, the total vapor pressure becomes equal to P naught A into XA plus P naught B into XB, where P naught A and P naught B are the vapor pressure of pure component A and B, and XA and XB are mole fraction of the components A and B in the liquid phase. I hope everybody know this now. Sir, then if this law is followed, this law is combination of Raoult's law and Dalton's law. So if this law is followed by any type of solution, then that solution is termed as ideal solution. So if any solution who follows Raoult's law, at all range of temperature and composition, as in this Xa and Xb are mole fraction of component A and B in liquid solution. Sir, technically, because we are reading, I mean, this is our personal class, we'll not speak it outside. We say it Xa and Xb because this is GSA way, Gaurav Singh Arora way of easily iterating what is X and XB, which are mole fraction of A and B in liquid solution. But technically, Shashi Tharoor, if will come and he'll read, he'll say chi A and chi B. So you should not be getting confused. This mole fraction is by the Greek name of this abbreviation is chi A and chi B. But I rather like saying Xa and Xb. Now, so if this total pressure is coming out to be as calculated by Raoult's law, then the solution is called an ideal solution. And for an ideal solution, delta H mixing and delta V mixing, as in when you mix two solutions, there is no enthalpy change, and initial volume and final volume will remain the same. Therefore, delta V mixing is also zero. Now, what about other thermodynamic terms, sir? Beta, delta S is entropy change. Sir, if you mix two components, then initially there were only component A, now it is more component B, so more people, they will shout more and they will always create more randomness. So whenever you mix component A and B in a solution, the beaker will have more entropy because more members are participating inside the solution. Therefore, entropy change on mixing is always positive because entropy will increase. What about delta H mixing? Sir, when you mix two solutions, then obviously they are spontaneously mixed. When you are mixing two components and they are easily mixing with each other, forming ideal solution, then it is happening spontaneously. And all the reactions which happen spontaneously, thermodynamics says that they have negative value of Gibbs free energy change. So delta G mixing will always be negative. These are some important thermodynamic operators and their conclusions that you should know for an ideal solution. Okay. Yes, beta. Art Art Y native. So Art Y native is asking, change in entropy is always positive in mixing. Yes, beta. Change, once you mix, either you get a non-ideal solution still because they are mixing by themselves. Therefore, delta G will always be negative. And because once you mix, sir, components will increase. Initially, there was only one person in the room. Now there are more than one person, so obviously entropy will always be positive on mixing, either for ideal solution or for non-ideal solution. Then sir, what will be different for non-ideal solution? Now I will come to this example, but what will be different for non-ideal solution? I'll be coming to this. For non-ideal solution, the total pressure which you actually calculate with will either be less than or will be greater than what, sir? Then you have calculated what we have calculated, P naught A XA plus P naught B XP. So if I am less than the calculated value as per Raoult's law, then that means I am showing less pressure. And if I am showing less pressure, then this means I am showing negative deviation from Raoult's law. And rather, if this pressure of solution is more than the calculated value, then this is termed as non-ideal solution showing positive deviation from Raoult's law, and this is negative deviation from Raoult's law. Now, some theoretical questions which JEE also throws us around it. Why you have ideal solution? Generally, we have ideal solution because the AA interaction and BB interaction, once AB is mixed, the AB interaction is of same magnitude, as in the intermolecular attractions are same. Sir, how can intermolecular attractions between two different molecule will be same once they belong to approximately same functional group? Like for example, if you just think of the example of ideal solutions, they are homologues. What are homologues? Just one carbon, just to add or subtract one carbon, the functional group, their reactivity, their physical property are more or less same. Therefore, they are more or less ideal. If you ask me practically, then beta, practically there is no person called ideal person, there is no teacher called ideal teacher, there is no student called ideal student, there is no gas called ideal gas practically. So similarly, there is no solution which is ideal. But yes, who are these approximately ideal solutions which are belonging to same functional group? So benzene and toluene both are aromatic hydrocarbons. Hexane and heptane both are alkanes, so saturated hydrocarbons. Then ethyl bromide and ethyl iodides, they both are alkyl halides. Then you have chlorobenzene and bromobenzene, both are aryl halides. So all these are basic examples of ideal solution, because in your JEE examination also, even a question is asked out of you that which of the following is what. So you should, a very important point. Moving to non-ideal. Moving to the graph now, sir, why we should see it graphically? Because for an ideal solution, sir, you already told us that pressure of solution is exactly same as calculated by Raoult's law. So what does Raoult said? Raoult said that partial pressure of A, once you mix, it will be equal to P naught A into XA, and partial pressure of B will be equal to P naught B into XB. So obviously, total pressure, which is pressure of solution, will be equal to partial pressure of A plus partial pressure of B. If you just put this, you will get the ideal solution mathematical equation. Why? Because pressure of solution will be exactly same as per calculated by Raoult's law. Now let us plot it graphically. If we plot mole fraction of component A and B in liquid phase in x-axis, and rather plot the vapor pressure in y-axis, so this is mole fraction and this is vapor pressure of solution or vapor pressure. If we just observe this plot beta, let's say here XA is 0. So XA is 0, so partial pressure of A will be 0. If XA is 1 over here, that means partial pressure of A, XA is 1, it is P naught A. Okay, sir. I hope. Then, sir, it is a straight line. So straight line drawn. Now, similarly, let us do it for partial pressure of B at XB is equal to 0, sir. But here only XA is written. Beta, for a solution, mole fraction summation is always 1. So if here at extreme right, I have written XA, which is 1, that means XB will be 0. So that means here, sir, XB will be 1. So it will be a straight line where where partial pressure of B will be 0. And here partial pressure of B will be equal to P naught B. That means, sir, this is a graph for partial pressure of A. And this is the graph for, this is the straight line, obviously a straight line, y is equal to mx form for partial pressure of B. Now, sir, if you add both the straight lines, you will again get a straight line. So this is your straight line. Which is my straight line? This is my straight line. And this straight line represents what? So this straight line represents the partial pressure of solution, which is nothing but partial pressure of A plus partial pressure of B. So as per Raoult's law, if a solution is exactly following this straight line graph, then this means it is a graph for ideal solution. I hope everybody is with me in this. Now, moving to this crucial part, because most of the students learn this. Now, I will not suggest you to learn this. At least don't learn this, try and understand this. Sir, how to understand? Let me help you with it. Now, suppose I am now plotting XA also, as in partial pressure, as in mole fraction of A, or maybe B. Sir, if it is XA, then XB can also be written. How? Let's say here it is showing P naught B. Okay, sir. If it is showing it is showing P naught A, that means here XA is the only entity. So XA is 1. That means here XB is 0. So what about this side, sir? Here XA will be 0. That means XB will be 1, because mole fraction of A and B in liquid phase is obviously 1. So, sir, here that means you are only plotting mole fraction of A and B in liquid phase. Yes, for now, time being, I'm only discussing that now. Sir, we have already seen the pressure of solution is a straight line. Sir, the straight line is already drawn. Let me change the color of that straight line. Let me make it yellow. Acha, I have this option also na, of drawing straight line beautifully. So let me draw the straight line beautifully. Okay, sir. I have drawn this. This is my straight line, that is, this is my plot of complete pressure of solution with respect to chi A and chi B, which is X and XB, which is mole fraction of A and B in liquid phase. Now, sir, what is this? Beta, if you, for example, because we have done this derivation in the previous class also, you tell me, for example, if I have a liquid solution, here I have A also and B also. So this is a liquid solution having A and B. If I bring it to temperature T, you tell me whether it will form some vapors. Yes, sir, it will definitely form some vapors. So what those vapors will be? Sir, let us show those vapors. Let us say these are those vapors. So XA and XB are mole fraction of A and B in liquid phase, sir, but they will produce some vapors, and those vapors will create this vapor pressure. So let's say the mole fraction of component A and B in vapor phase, which I'm writing with the pink color, let us represent the mole fraction of A and B in vapor phase as YA and YB. Sir, we can definitely do it. Now you tell me, can you take out these vapors? Yes, sir. If you connect it with a duct, these vapors will be extracted out. And if I extract out in a different beaker, sir, and then if I cool them, then all these vapors, sir, they will get, okay, sir, now these vapors will get liquefied. So whatever was YA and YB will become XA and XB, but of the second container. I hope everybody is with me in this. Now, if I bring the YA and YB, which I have condensed in liquid form, and now if I take this to temperature T, they will again form some vapors. But these, let's say this is XA and XB, and this XA is nothing but YA, this new XB is nothing but YB. They will again form some vapors, sir. Now let us say those vapors have mole fraction YA dash and YB dash. This XA is nothing but, sir, this XA is nothing but YA. This XB is nothing but YB. Why? Because I have condensed these vapors into another second container. So in this second container, sir, that means you are extracting them. Yes. Now you tell me here, who will come more? Who will be coming more, sir? If out of A and B, whatever is more here will be more here as well. Now you tell me among A and B, who will be more? Sir, because you have assumed, because I have assumed, now I'm asking you, What is at the same temperature T, what is the value of P naught B? Sir, value of P naught B is by magnitude, it is less. And value of P naught A at the same temperature is more. That means vapor pressure of component A is more. That means liquid A is easily making those vapors. That means the molecule of A and B are not very much attracted to each other. That means, sir, A is more volatile. It is eager to form vapors. That means it will have less boiling point. So with this graph, I can also conclude that A is more volatile than B. Obviously, I must have assumed this, then I have drawn this graph. A is more volatile than B, or else you can say boiling point of component A is less than boiling point of component B. I hope with this conclusion you can say that, but sir, still, yes, Mr. Native, yes. Sir, something, beta, this is definitely high weighted chapter, beta. I am answering to YKBVS, beta. Why you keep so critical names? Nupur was saying hi, so Nupur, hi from my side, from me as well. Sir, explain more deeply as the I'm doing the same origami, whatever. Then last is crafts. Then Shlok Pandey is saying, sir, can you please say my name? My name is Shlok. Shlok, I am very happy to announce your name. Your name is Shlok. Welcome, but take out your pen and copy and start studying. Yeah, so this is why, sir, why you are explaining this this case of condensation, because with this I'm trying to tell you that once you have XA corresponding to this XA, you can find value of Y. What I'm saying is, once you have value of XA, once you have value of any random value of XA corresponding to that value of XA, you will get a pressure. This is pressure of solution. Corresponding to that value of XA, you will get pressure of solution. That XA can be converted to Why? Sir, because corresponding to a value of XA, let's say value of XA is something here, whatever it is. Can I calculate YA for this XA? Yes, sir. We have done this in the previous class. What was the formula? Sir, pressure of solution into YA is nothing but partial pressure of A. And according to Raoult's law, partial pressure of A is P naught A into XA. So corresponding to every value of XA, I can find value of YA, which will have the same total pressure. So corresponding to each value of XA, I can have some total pressure. And corresponding to that total pressure, I will definitely have some value of Y. Beta, this pink line is that point, which is the corresponding value of Y. Now what I'm doing? I am converting these YA vapors and condensing them and making them a new solution. So now that YA has become XA. So now this value of corresponding to this, corresponding to this XA, now I'm converting that XA, which has converted to YA. Sir, for every XA, for every value of XA, I can have a corresponding value of YA also. So for that YA, what is the total pressure? This is the total pressure. That YA can be converted, that XA can be converted to YA. That XA can be converted to YA, and this YA I am liquefying, which is now converting to mole fraction of that A in liquid phase. So this is now converting to mole fraction of A in liquid phase corresponding to the same pressure. So that is now corresponding to mole fraction in liquid phase. And again, corresponding to that value, I can do that. So that means ultimately you are reaching here. That means, sir, the component which is more volatile, will be getting separated. Sir, obviously, the component which is more volatile will be coming out more. And once you keep on doing that, you can separate that A from B. So that is the logic also to have fractional distillation of two components which have different boiling points. So what this graph is telling us, that mole fraction of A, mole fraction in liquid phase and mole fraction in gaseous phase, once you plot, they can be plotted in the same line and it will be a curve. Mole fraction of total pressure, the graph of total pressure with respect to mole fraction in liquid phase will be a straight line. But graph of total pressure with respect to mole fraction in gaseous phase will be a curve. Sir, mathematically prove it. You can obviously see it. This is total pressure and this is mole fraction in gaseous phase. Sir, it is y is equal to x type, as in it is an exponential curve. It is not a straight line. So even for an ideal solution, you can get a curve. Most of the student feel, sir, if I'm getting a curve, then this is definitely a non-ideal solution. No, it is a straight line for an, it is the curve for pressure with respect to mole fraction in liquid phase is a straight line for an ideal solution. But the curve, the graph for vapor pressure with mole fraction in vapor phase is not a straight line, my friends. It's a curve. I hope everybody is clear with this. I hope everybody is clear with this, guys. Guys, this is good. This is important thing. The only important thing which generally teacher do not communicate to students, that even for an ideal solution, you can have a straight line also and a curve also. Because straight line will be a graph when you are taking mole fraction in liquid phase. For the same liquid solution, you can have a curve because the same pressure with mole fraction of component A and B in gaseous phase will be a curve, will not be a straight line. I hope, beta, I need whoever is here. I mean, yes, I see most of you will be watching this in a recorded format, and definitely I understand that also. But whoever is there, kindly reply. Hi, sir, I am Parnika. Happy birthday? Whose birthday? Nobody is having birthday today. No. Chalo. Done. Done. I need confirmation, guys. Guys. Yes. Harshit. Good. Chalo. I hope you got this much, right? Chalo. Moving forward. Now, sir, then you already, sir, that means now we can move to non-ideal solution, obviously. Once you have non-ideal solution, that means, sir, you can have positive deviation or negative deviation. What is positive deviation? Sir, now we can have deviations. Why will have deviation? That too positive deviation, because A and B once mixed, they are not liking each other, and that's why they are running away from each other. So they will come in vapor phase to a larger extent, and because they will come in vapor phase, sir, you told in class, okay, so Yogesh is our Laksh batch student, that means. So acha, okay, Parnika, yes, Parnika, okay. So beta, that was a message inside the class. This is outside. Yes, so thank you, Parnika, thank you. Although after 30, birthdays are, I mean, no one wants to get old. So anyways, sir, you OP. Sir, you OP? Yes, sir. Okay, chalo, moving forward. Now, sir, non-ideal solution showing positive deviation. Sir, when you will show positive? When you will have more pressure. Why are you having more pressure? Because interaction between AB is weaker than AA and BB. Then during positive deviation, what we have? Sir, delta H will also be positive. Delta V mixing will also be positive. And again, these and thermodynamic variables remain the same. Entropy will increase. Gibbs free energy will decrease. Just like non-ideal solution, just like ideal solution. Because, sir, on mixing, these two thermodynamic variables always remain. This increases and this decreases. I hope everybody is clear. Now, sir, what shall be the graph? This is obviously for the ideal case, but sir, because I am having more vapor pressure, so these are non-ideal solutions showing positive deviation. So let us talk about positive deviation first. That means, sir, partial pressure of A will also be not that much, it will be more. Similarly, partial pressure, so B will also be running away from A. So total pressure, let me draw that total pressure with a separate different color. So the total pressure will also be more than what you calculate as per Raoult's law. So this is your graph, but now this is a curve. Why this is a curve? This is a curve for pressure of solution and mole fraction of component A and B in liquid phase. Sir, can we have the same graph in for vapor phase? Yes, but we will be making it separately. I hope everybody is clear now. हाँ बेटा, IIT and this is solution because we left colligative property in the previous class, so I'm just finishing colligative properties and then we'll quickly start electrochemistry. Now, sir, for non-ideal solution showing positive deviation from Raoult's law, what are the options? Now, a trick, a very smart trick. When you will have negative deviation, sir, the only reason and the only way we can have negative deviation when AB interaction is more. When you can have more interaction between two different molecules, whenever you have a strong bonding. Sir, what is the basic example of a strong physical force of attraction? It is always hydrogen bonding. So whenever in your options you get such examples which have some special hydrogen bonding attraction between them, then those solutions will only show negative deviation because they are attracting each other, so they will form less vapors. Obviously these thermodynamic factors will remain the same, but sir, what will happen? Beta, they will have less pressure because A will be loving B, so it will be going less in vapor phase. B will also be showing less, so this will be a negatively deviated curve as per ideal solution. And sir, what are the example of solutions showing negative deviation? The famous example, beta. If you just learn these examples, no question is going to challenge you. Sir, then that means for ideal solution, you should just see they belong to same function group. For negative deviation, these are the famous examples. What are them, sir? I guess this is white and white, so it must not be getting much visible to you. But yes, once you take these lecture notes, sir, how to download these lecture notes, just go to PW JEE English WhatsApp channel. You can download these notes. Once the live is done, I'll be pushing these notes in the WhatsApp channel. But yes, then you can clearly see it. But I guess it is more or less, or let me iterate it, beta. This is chloroform and acetone. This is chloroform and benzene. This is chloroform and diethyl ether. This is water and HCl. This is acetone and aniline. This is phenol with aniline. This is water and nitric acid. This is pyridine and acetic acid. Sir, why such a strong attraction force is happening between them? Let me just give you a basic example. The famous example is for negative deviation, chloroform, sir, which is CHCl3, and acetone, which is propane 2-one. Everybody know that because carbon is connected with 3 electronegative chlorines, so this will make carbon electronegative, and therefore this will have a capacity to withdraw the electron density of hydrogen, thereby producing positivity in hydrogen. And here the carbonyl group is highly polar, so this minus plus will start attracting each other, and this minus plus attraction creates the AB interaction. This is the AB interaction. This is molecule A, this is molecule B, and this AB interaction is stronger than individual AA interaction and BB interaction. So all those examples are best examples, are best known examples of solution showing negative deviation. And sir, what will be the example of positive deviation? All the other cases. So for ideal solution, it should belong to same functional group. For negative deviation, you should have special hydrogen bonding and all the other cases. So let me give you the examples also. Now you can very well attempt these type of questions just by learning through this conceptual thing. So what are the examples, sir? So like acetone and carbon disulfide, although also you can generalize it using chemical bonding knowledge. Sir, carbon disulfide is a linear molecule, so it is non-polar. Sir, acetone, we have already seen it is polar. So polar and non-polar, sir, why they will like each other? They will run away from each other. Similarly, you can see these examples and they will be helping you like anything. So with this, we have Huh. So with this, we have completed ideal and non-ideal solutions. Sir, what about questions? But obviously, I'm giving you these questions also. You will be finding answers also over here. So, but yes, because we have to cover a chunk of a chunk of parts, so we shall, if we get time, we'll discuss these questions in the end. But rather, I would want for the conceptual discussion first, है ना? So, hello, sir. Yes, Varun. Hello, beta. Good evening. Then, sir, this isn't part of Electrono beta as I've communicated, Varun. First, I'll be finishing the part we left in the previous live, that is the colligative properties, and then we'll be starting with electro. Chalo. Now, sir, this distillation thing you have already explained us that if A is more volatile, then ultimately it will be getting separated. So when it will be done when A is more volatile. So that distillation thing can be understood with the help of this graph, which I've already explained. Again, a very good question, rather a very good question. So a very good question, but yes, you can obviously practice it, and if you find problem, you can obviously go to the description section, and once the live is done, hit the comment section. Sir, we want discussion of the questions as well, and definitely I'll be, but this is a good question, beta. Please try this one. Chalo. Now, sir, now we know what is ideal solution and non-ideal solution. So mixture of two volatile liquids are, sir, if there are liquids, they are always miscible? No, not always. Not always. I hope you have seen the I mean, in the Diwali, most of the people do it. What? First they put water. What they do is, first they put water in a transparent glass jar, because water has more density, so it is always settled at the bottom, and then they pour oil, and in that oil, because oil has less density, so it is always floating. And once they do that, they put a wax, I mean a bati, and then they make it then they burn it, and obviously this beautiful diya is evolved, although this much is only oil and this is water. So sir, it is also liquid, it is also liquid. That means, sir, we have some liquids, oil is also liquid, water is also liquid, but they are not mixing, sir. That means, sir, you can mix two volatile liquids which are which are immiscible, which are not mixed, and very rare, but yes, JEE throws question around this also. So you tell me, have they become a mixture? No. So if you mix them, let's say this is component A, this is component B, and I have mixed them, this is A and B combined. Sir, but then, sir, but A is separated only. So if I am alone, although I am mixed with B, but I have no business with B. I am just still my same solution. So what will be mole fraction of A here? Beta, mole fraction of A as in moles of A in liquid phase upon total. Sir, I am not even mixing. So XA is completely one, although they are introduced in the same container, but still I only have moles of A among all the moles of A. I only have moles of B among all the moles of B. Sir, we are not even mixing. So XA and XB both are one. That is it, sir. Then you apply. Then you, sir, you are putting a temperature T. We are liquid. Then as per our temperature and boiling point, we will form vapors because we have no business with each other. That means, sir, formula will remain the same. What will be pressure of solution? So P naught A plus P naught B. Why? Sir, why you are not writing XA and XB? Because they are one. They are immiscible. How can you calculate mole fraction of A in vapor phase? Sir, it is pressure of solution that you already know. And it will be partial pressure of A, because this is partial pressure of A as per Dalton's law. So partial pressure of A as per Raoult's law will be P naught A into XA. Sir, you again do not have to write XA. So this is how you can simply find mole fraction of A in vapor phase. So these questions are definitely asked, that what will be mole fraction of A in vapor phase, or rather they ask you this. So mole fraction of B in vapor phase will be equal to, so PS will again be here and it will be P naught B. So if you just divide it, what you will get? Sir, PS is cancelled. this is mole fraction, this is number of moles of A upon total moles. Total will be cancelled, so this will be moles of A in vapor phase upon moles of B in vapor phase. So because this is vapor phase, so I'm writing dash, because generally we write Na and B moles in liquid phase, and it will be equal to P naught of A upon P naught of B. Suppose weight is given. So you can calculate molar mass. A similar question came in JEE. See, the weight is given. It is 75% by weight of water. So the distillate, as in the vapor composition, is given. So vapor composition was 75% by weight of water. So if total mole fraction was whatever, 75% of the weight was water. So you can obviously apply that in the formula and you can solve such questions. So these are for immiscible liquids. Again, Anya Rani. Okay, I hope everybody is clear. So again, I'm giving questions for practice beta, but yes, questions you have to attempt. And once you attempt, if you find problem, you can obviously once the live is done, this will be there, because I know most of you will be watching this in the recorded version. So you can obviously go to the comment section, hit the whatever doubts you have, whatever more you want out of these things, and definitely I'll be coming. But I want your participation as well, because I am not having that level of participation in the comment section. So obviously I know that I'll be having that level of participation once you will be watching this in recorded version. Now, sir, you said I will be discussing the graph of mole fraction of in liquid phase and vapor phase in the later session, in the later slides. Now we have reached to the later slide. Now what happened is, so this graph we have already seen. It is for ideal solution. This is mole fraction in liquid phase, and this is graph of ideal solution with total pressure for mole fraction in vapor phase. So this we have already seen. Okay, sir. This is a straight line. This is a curve. Now, once you, sir, in nature you said there is no ideal solution. There is approximately ideal solutions you have, but I'm exactly ideal, you know. Then in nature what we have? In nature we only have non-ideal solution. In nature we only have legend. Hi sir, you are great. I cannot comment because watching lecture. No worries, beta. If you are learning, I'm completely happy. No requirement of any comment, beta. Just learn. Thank you. You wrote that, and it has given me a spark. So thank you. Chalo. Now, sir, that means this is graph for ideal solution. Okay, sir. But sir, in nature we do not have. We only have non-ideal solution. So if you have non-ideal solution, no matter, it is showing negative deviation or positive deviation. If you start plotting this graph for non-ideal solution, no matter negative or positive, if it is weakly negative or positive, as in the intermolecular attractions are weak enough, that means it is weakly deviated from Raoult's law, as in pressure of solution is little bit, slightly more or less than as per calculated by Raoult's law, then we got this graph. Okay, sir. I mean, the curve was just the same, but yes, instead of the straight line, I have for XA also I've got a curve. So this is for negative deviation. So for Y it is already a curve, but for X also it become a curve because it was a positively deviated solution. I hope. But sir, once we have plotted this graph for solutions, non-ideal solutions, which are showing large negative and positive deviations, we were blown. Not for all non-ideal solutions, but for few non-ideal solutions showing strong negative and strong positive deviation, we were blown. Why? Because we got a graph where mole fraction of components in liquid and vapor phase are getting equal. Mole fraction of liquid and vapor phase are getting equal here because they are meeting at this point. That means value of XA, value of mole fraction in liquid phase and mole fraction in gaseous phase is becoming same, and the solution is the solution has become a single component. Because see na, they are meeting at a point. That means, sir, mole fraction of components in liquid phase and vapor phase have become same. Such a non-ideal solution such a non-ideal solution which are showing not weak but large either positive or negative deviation from Raoult's law at a particular composition, not at every situation, at a particular composition, they start to behave as a single solvent. You have mixed A, you have mixed B, but at a particular composition, this A and B, now they are some another solvent C. Why? Because they are having same mole fraction in liquid phase also and vapor phase also. That those non-ideal solutions are known as azeotropic mixture. Those are known as azeotropic mixture. Now, let us, okay, so I hope I have represented that. Yes, you can understand it very properly through that. But yes, that condensation and distillation altogether takes different I mean much of time. I mean, again, you can see, you can do that, that for a corresponding value you can again move forward. For that value you will again move forward. For that value you will again move forward, and ultimately you will be landing here. Similarly, if you'll start for another species, again you will be landing directly here. So my point is, I mean, just I'm not I'm not doing it completely, because obviously we have to make it precise also, that they will not be getting separated. They will reach this point either from this side or that side. That means now this mixture will never be separated. This will have same composition throughout. Once they have reached that particular composition level, which is actually termed as azeotropic composition. So let me define azeotropes for you. So what is azeotropic mixture? A binary solution containing two volatile liquid in which both the liquid and vapor have same composition. X and Y have same composition. A boiling liquid mixture at azeotropic composition produces the vapors of exactly same composition. That means value of XA and YA becomes the same. Value of XB and YB becomes the same. Now, sir, how many type of azeotropic mixture we can have? Just the two types. Sir, how to remember it? Now, the first one is minimum boiling azeotrope. What are minimum boiling azeotrope? Again, sir, they have to be a non-ideal solution. But showing what? Now, how to remember this? What does minimum boiling mean? Minimum boiling means my boiling point is less than the boiling point of the individual component. My boiling point is less. When will I boil at a lesser boiling point? When I will be giving more, I mean, boiling as in the pressure at which my pressure becomes equal to atmospheric pressure. But if I'm ready to boil at a lesser temperature, that means I am creating the equal amount of vapors, equal to vapor pressure, equal to atmospheric pressure at lower temperature. That means that I must be showing very high positive deviation from Raoult's law. That means I must be showing highly positive deviation from Raoult's law. So if a solution is showing high positive deviation from Raoult's law, what type of non-ideal solution I should have? A non-ideal solution which is showing high positive deviation from Raoult's law can only form a minimum boiling azeotropic mixture. Sir, can you give us an example? Beta, not, I mean, this example is not important. It is very important. Okay. What is it? Sir, water and ethanol. What is the composition? Sir, water has to be approximately 5.6% and ethanol have to be approximately 94.4%. So if water is approximately 5% or maybe 6%, exact percentage I have written, and ethanol is 95%. So at this particular composition, water and ethanol start to behave as a constant boiling mixture. And the boiling point of this mixture at this particular composition is even lesser, minimum, than the boiling point of their individual component. What is the boiling point of ethanol? Sir, it is 351.5 Kelvin, less than 100 degrees Celsius. What is boiling point of water? Sir, it is 370. Obviously, this is 373, not 375, 373. Because 100 degrees Celsius plus 273. So precisely it will be 373.15. But what is the boiling point of this azeotropic mixture? It is 351, even less than boiling point of individual components. And why? Because water and ethanol mixes and form what type of solution? They mixes and form a positive deviation from Raoult's law. I hope everybody is clear. I hope everybody is clear. Now, after minimum boiling, let us learn maximum boiling. So maximum boiling, again, do the vice versa thing in your mind. Sir, maximum boiling azeotropic mixture, as in as a mixture, our boiling point will be more than the boiling point of individual components. Why my boiling point will be more? Because I will be giving pressure equal to atmospheric pressure at a higher temperature. That means I must be very much in love with the component with which I have been mixed. That means it will be formed by those non-ideal solutions which will be showing negative deviation from Raoult's law, and hence I'll be showing positive maximum boiling azeotropes or maximum boiling azeotropic mixture. I hope everybody is clear. Sir, give us an example, beta. Very famous example again, water and nitric acid. At what particular composition? Water and nitric acid at the percentage is not written over here. Let me just write it. Nitric acid should be nitric acid which has a boiling point of 359. It has to be around 68%. This is HNO3. And water with boiling point this much should be obviously 100 minus this. That means it should be 32%. And once they reach this composition as a nitric acid 68%, water 32%, they behave as a constant boiling mixture, and this constant boiling mixture has a boiling point which is even greater than the boiling point of individual components. This is this. Why? Why, sir? Because they are forming negative, because they are having negative deviation from Raoult's law. That means they are attracted to each other, and because they are attracted to each other, so they are forming less vapors. So in order to form the vapors which is exactly equal to atmospheric pressure, I have to supply more temperature. And that's why boiling temperature, the constant boiling mixture is having high temperature, which you should learn the value also. It is 393, because this is a very famous NCRT. This is a very famous NCRT conclusion. I hope everybody is clear. Chalo. Moving forward. Graph also I've given you. Now, quickly coming to colligative properties. Now, because now one colligative property we know, RLVP, relative lowering of vapor pressure. Let me revise. Let me make you revise RLVP quite quickly. Okay, let me do it here only. So, colligative properties, they are properties which depend only on the number of solute particles, not on the nature of particles. Condition, solute should be non-volatile, and solution should be dilute, because for dilute solution only colligative properties is valid. Again, a concentration term for dilute solution. For dilute solution, beta, molarity is approximately equal to molality. So you need not bother whether molarity is given or molality is given. Now, what are these colligative properties? Among them, the first colligative property is relative lowering of vapor pressure, which is nothing but P naught minus Ps upon P naught, which is equal to mole fraction of solute. For solute, I write as 2. So it will be equal to number of moles of solute upon number of moles of solute plus number of moles of solvent. This I have discussed in my previous live, so not discussing much about it. What is the second colligative property? I am being quick over here. Sir, once you have added a non-volatile solid solute in a volatile solvent, similarly that we have discussed, sir, pressure is decreased. Now, if I want the same atmospheric pressure, then I have to apply more temperature, more heat. So whenever you add a non-volatile solid solute in a volatile solvent, the boiling point of the solution is elevated, and that elevation is termed as delta TB, which is elevation in boiling point, which is nothing but boiling point of solution minus boiling point of solvent, and it is directly, now this is a statistical formula, beta. Once we have found out that as we increase the amount of solid solute, this boiling point elevation as in difference also increased. We were confused why it is increasing. The plot showed as you increase the concentration, and what concentration, what concentration term was designed, I mean it is a statistical analysis, the concentration term was molality. So the moment you increased molality, elevation in boiling point also increased, and it was experimentally statistically observed that it was a straight line, so they are directly proportional. The proportionality constant for y is equal to mx type, so what will be m? What was m? The m came out to be a constant which was a characteristic for the solvent. As you change the solvent, this value changed, and to this value, in case of boiling, we call it ebullioscopic constant, as in boiling point elevation constant, or somebody even call it molar elevation constant. This is the value of Kb. Now, sir, similarly, if you add non-volatile solid solute in a volatile solvent, then sir, solid is already there, and if you now want to decrease if you now want to make the solvent solidified, then sir, you have to take out the heat. That means you have to decrease the temperature. So solvent will give heat and will solidify, but sir, the solid which is already in solid form will also give heat because it will also cool down, but sir, it is already solid. So that means you have to draw more amount of heat, and in order to draw more amount of heat, you have to even lower the temperature, and therefore boiling point gets elevated but freezing point gets depressed, and this depression in freezing point is termed as written as delta TF. Change is always positive, so this is solvent minus solution. For not, I'm writing as solvent. For simple, I'm writing solution, I'm writing TF, and this also came out to be equal to KF into molality. That means this was also directly proportional to concentration term. What concentration term? Molality. Kb and Kf are ebullioscopic constant and cryoscopic constant, which are only a characteristic of the solvent. You change solute, Kf has no different, is indifferent with it. That means Kf and Kb are the characteristic of pure solvent, of the solvent onto which you are adding non-volatile solute. So these are the three colligative properties. Now, what is the fourth colligative property, sir? Okay, let me just show you in the slides. Now this Oswald-Volcker method you can obviously leave for time being. This is valid but only for advanced. So Oswald-Volcker method, elevation and boiling point I've already explained you. Yes, the graph. This graph actually was the experimental thing that told us that for solvent, boiling point was this. But as I have added some W1 amount of solute, the boiling point got increased, and this becomes your elevation in boiling point. Similarly, if I have added more solute, W2, so this solution will be solution 2, the boiling point was more elevated. So let's say this is delta TB1, this is delta TB2. So this graph actually told us that there is an elevation in boiling point, a very famous graph from NCERT. Sir, you said Kf and Kb are characteristics of solvent. So a very famous formula, how to remember it? You remote. So learn this, remote. So instead of this, you should learn it as RMT, as in remote, RMT. So remote, RMT, R is universal gas constant, M is molar mass of solvent. So because solvent, so I'm writing 1. T is, because we are talking of boiling, so this is boiling point of solvent. So TB0 is how represent a boiling point, and square of this upon delta H, which is enthalpy of vaporization of that particular solvent, into 1000. Obviously, what value of R you will use? Sir, in calorie it will be 2, in joule it will be 8.314, depending upon what is the value of delta H vaporization given. I hope everybody is clear. Now, similarly, sir, depression in freezing point. Sir, freezing point is the temperature at which vapor pressure of a solvent becomes equal to vapor pressure of a solid. Solid also has vapor pressure, all the very less. So this will be the freezing point of solvent. Now, if I'm adding non-volatile solid solute, then freezing point is getting depressed. So if I have added W1 amount of solute, see, now at what temperature? corresponding to what temperature the vapor pressure of liquid solution and solid solution has become equal? Sir, at this point, that means this will be my freezing point of the solution having W1 gram of solute. So you can obviously see this is, let's say this is TF naught, so this is delta TF. If I have added more solute, then the other solution showed that the freezing point was depressed to a larger magnitude. So this is delta TF when solute is more, this is delta TF when solute is less, and this is depression in freezing point. I hope everybody is clear. Very beautiful graphs from NCERT. Now, freezing point definitions, which I have communicated, I've already written. This, I mean, yes, you can understand that there is depression with some other explanation also, but I guess let me leave it. This is good. The formula again, sir, RMT square. So Rm of for solvent, this is freezing point of solvent squared upon delta H 1000 into delta H fusion. Why? Sir, because when liquid changes to solid, that is a phenomenon of fusion. So delta H fusion, as per the data given, whether it is in joule or calorie, accordingly you'll put the value of R and you can calculate the value of Kf and Kb for that particular solvent. Yes. For water beta, most of the time it is given in the question, but yes, I advise for water you should learn this value. So for water, value of Kf is 1.86 Kelvin kg per mole, and for water, value of Kb is 0.52 Kelvin kg per mole. So at least for water as a solvent, you should learn the value of ebullioscopic constant and cryoscopic constant moving forward. Now, these are again questions, beta. I obviously, so these are obviously homework questions for you. Again, these beta, they are directly the questions. They are directly the questions from JEE Mains and Advanced, and just the formula that I have told you, just put the formula and it will be done. So because I need participation, so if you want, if you want the discussion, then after the live, you know what to do. Come on. Now, good. Again, a very nice concept of ice separation. Let us do this because students are fearful of this topic. So concept of ice separation, let us do this with the question. So this is a JEE Mains 2019 question, and the question says that a solution contains 62 gram of ethylene glycol. Okay, so this is the weight of solute in 250 gram of solvent. Okay, sir. So this is my weight of solute as in W2. This is my weight of solvent as in W1. And it is cooled up to minus 10 degrees Celsius. Okay, sir. That means you're cooling after adding a non-volatile solute, you're cooling your solution. Obviously, sir, the freezing point will be depressed because for water, freezing point is 0 degrees Celsius. Because I have added ethylene glycol, the freezing point has depressed. That is why we add ethylene glycol in solution, because we want freezing point to be depressed, or else the engine oil in the cold countries will be frozen. So we want the engine oil to be in liquid form. So we add non-volatile solute so that the engine will keep on functioning. It will not turn solid in a cold region, because obviously in those snow area also you see the cars running. So sir, how those cars are running? The water, the coolant, the engine oil, all things should get solidified, but they are in liquid state. Why? Depression in freezing point logic must have been applied in the content that has been taken inside it. So that depression in freezing point. Okay, sir. So sir, out of this 250 gram of water, some of the water must have solidified and would have formed ice. Why you're saying some, sir? Because this is the freezing point, and at this freezing point, some of the, how much water I have taken, this was the solvent, and once this much of solvent was added with this much amount of solute, it was cooled up to minus 10 degrees Celsius. So once it was cooled, beta, some of the liquid water must have been solidified. Sir, what amount has been solidified? I do not know. So let us apply that formula. What formula, sir? Delta TF is equal to Kf into molality. What is delta TF, sir? Solvent minus solute, solvent minus solution. So for solution, it is saying minus 10. So obviously I can directly write plus 10, but because we are doing for the first time, so I'm telling you delta TF is 10. Sir, but it is degrees Celsius. You should convert in Kelvin. Don't make this mistake in such questions. Don't make this mistake in such questions. Oh, okay. Sumit sir, thank you. Yes, thank you, Sumit sir. Oh, chalo, perfect. Although we have very less participation, sir, but still we are working because I know many of the students will be watching this in the recorded version. So this is our moral obligation that no matter if any student is waking up at 2 a.m. in the morning and want to revise the one shot, then definitely, as promised, we should definitely uh, give them the best. So this is what each and every one of us are doing over here. Chalo, thank you, sir. Now, so delta TF is KF into molality. So delta TF is 10. Now what is KF, sir? For KF for water is 1.86. And what is molality? Number of moles of solute, which is weight of solute upon molar mass of solute. For ethylene glycol, I guess if you'll just solve, carbon is 12, 12 into 2 is 24, hydrogen is 2, 4, then 6, that means this is 30, and 16 into 2 is 32. So 30, so this is 62 only. So molar mass is just, see, this is JEE mains question, and this is what they do. They make you cancel the formula like anything. Sir, into divide is also easy. The denominator has weight of solvent in gram. Sir, I have taken in 2000, because this should be in kg. Sir, I have taken 250 gram of water. Once the solution is cooled, some of the water must have formed ice. That ice has been separated because density of ice is less, so ice would have been floated to the surface. Then still some of the liquid water will be remain. What water will be in the liquid form? Sir, this is weight of solvent in the liquid form till temperature 10 degrees Celsius. So that's why I've written W1. Now, if we solve this W1, which is, I guess this is quite easy to calculate also. So W1 will be equal to 0 and 0 is gone. So this will be equal to directly 186. That means, sir, if 250 gram of water you have added and freezed till minus 10 degrees Celsius, then whole of the 250 gram is not ice, sir. This much of water is still in liquid phase. This much of water is still in liquid phase. So what is the weight of ice that has been separated? Sir, water which you have used initially minus water which you have still in liquid phase, which is this. Sir, initially I have used 250 gram. Now it is just 186 gram of liquid water. That means the remainder, the difference is ice. So 4 and 60, 64. I hope everybody is clear. Okay, thank you. Thank you, Sanjit, Kumari. Thank you, King Suk. Why so less views? Beta, you don't promote. Although don't promote because we are here for you. So at least we are here, at least you are here, so everything is great. But hit the like button. Although we are told that don't say, but I have to say because we are putting in everything and you guys are not coming, going here, there, getting not good content, still not saying anything. But I know that. Thank you, thank you. Chalo, chalo. So King Suk, this is your fault. Come on now. I'm just kidding, beta. Thank you. At least you are here. Thank you. Nahin, beta, you study. You know what? You study, you get that best AIR, and then you just come in a video and you say that how we helped. That is it. So your best result is our best promotion. And that is why we are here, beta. So come on. Now, sir, the three colligative properties we have done. What three, sir? Sir, RLEB, delta TB, and delta TF. What else, sir? Last is osmosis. What is osmosis? Sir, the RO we already have in our household. What is RO meant for? What is RO meant for? Let me directly work on this graph. What is RO meant for? So here I have the same height of solution. That means here I have solute also and solvent also. Here I have solute also and solvent also. So that means I have solute and solvent solution. Of the same volume, I have solvent on the right side. Now you tell me, if I use a sieve, in your general life you must have seen that sieve, that filter, like a channi of the by which you make your chai, and in the morning how do you separate chai with the ingredients, the liquid chai with the tea with the ingredients. You just pass it in a sieve, the channi. That sieve is technically termed as a semi permeable membrane. That sieve is technically termed as a semi permeable membrane, and through that sieve only solvent can pass through because the pore size is very small. Solvent molecules are very small, but solid solute are bigger in size. Therefore, solute can't pass, but solvent can pass. Okay, sir. This separator is called as a semi-permeable membrane, which can be natural also, which can be artificial also. Artificial like the ferrocyanides and various salts. And what are these natural semi-permeable membranes? All the cell walls, the pig's bladder, the parchment paper. So they are all the semi-permeable membranes, the sieve, the channi that we have all around in nature. So we use those semi-permeable membrane. Now, what is allowed to pass through? Only solvent. Okay. So solvent is here, it is more. Here, solvent is less, because with solute it is attaining the same height. Okay, sir. Then things will flow from where? So from higher concentration towards lower concentration. So here concentration of solvent is large, here concentration of solvent is less. So solvent will flow from high concentration of solvent towards low concentration of solvent. And therefore, if solvent start flowing from high concentration of solvent towards lower concentration of solvent, the movement will take place. And if this is a massless piston, then it will move up. If you do not want this piston to move up, then you have to apply some external pressure. Sir, what is the pressure already there? Pressure of atmosphere. But because this is moving up, so apart from pressure of atmosphere, you have to apply some extra pressure. The amount of pressure I am applying on the solution side to stop the flow of solvent from solvent side to solution side is called osmotic pressure. And this process of flow is known as osmosis. Now, if I apply more pressure, then solvent will flow from this side to that side. So this is dirty water. That is pure water. This is what? RO, as in reverse osmosis, will start happening. Now, once we have started working on this pi, what we again experimentally found by iterating the amount of solute, we saw that this osmotic pressure pi was also directly proportional to the amount of solute I was adding. What was the concentration term? What was that was mathematically, statistically formulated? It was now C. That is molarity. This was not molality. And the proportionality constant came out to be RT. So it becomes CRT. So therefore, osmotic pressure pi is equal to CRT, where C is molarity of solution, number of moles of solute dissolved in solution. R is again the universal gas constant, and T is temperature of the solution in Kelvin. But here, obviously in Kelvin. So I hope everybody is clear with this too. Moving to, okay. Now, so these are the definitions, basic questions. Now, reverse osmosis, I have already explained. Now, what are isotonic, hypertonic and hypotonic solutions? What are these solutions? Isotonic, hypertonic and hypertonic solutions. Suppose I have a red blood cell over here. Suppose I have a red blood cell over here. Now, why I'm taking this red blood cell? Because this is a very beautiful NCERT example. This is a very beautiful NCERT example. Ekaf, thank you. Ekaf, I hope you have attempted all your DPPs, because for the Lakshya batch we have test. So I hope you are very much prepared for the for chapter solution. And yeah, although we had electrochemistry in the title, but we are discussing solution first. Why? Because during the previous live we could only finish concentration terms. So here I'm first finishing the job which was half done in the previous live, which is discussing the colligative properties. So we are just about to finish colligative properties. Here is the case. Eat this after the live. Thank you, Ekaf. I will definitely eat it. Thank you. Chalo. Now, red blood cell is also a type of solution which is enclosed in the cell walls. Our cell walls are semi-permeable membrane. So this semi-permeable membrane is dipped into a solution. What is the solution? This is 0.9% weight by volume NaCl solution. This saline solution is isotonic with the solution of inside red blood cell. What does isotonic mean? Isotonic mean vapor pressure outside is equal to vapor pressure inside. So not vapor pressure, I'm sorry, I beg your pardon, osmotic pressure. So what are isotonic solutions? Solutions which have same value of osmotic pressure are called isotonic solutions. And because RBC has exactly same osmotic pressure as 0.9% mass by volume NaCl solution, therefore they are termed as isotonic solutions. Point number one. They are termed as isotonic solutions. Point number one. Now, thank you, Sonia ji. Thank you. Now, they are termed as isotonic solutions. Now, sir, what is hypertonic and hypotonic? If I have a red blood cell and if I place that red blood cell in a saline solution which is having 1%, that means, sir, it is not 0.9%, is 1%. Yes, that means, sir, in the saline solution, solute is more. Let me write solute only. In saline solution, solute is now more. Sir, if solute is more, that means solvent is less. And sir, if solvent is less, that means solvent inside the red blood cell will be more. Therefore, solvent will flow out and the red blood cell will shrink. And this shrinking is biologically known as plasmolysis, or it is also known as crenation. Beta, these are some NCERT terminologies. Please invest time in them. Now, what is another English? Sir, that means if solute is more, so this saline solution will have more osmotic pressure, sir, because concentration more, so osmotic pressure more. So in this case, I will say saline solution is having more osmotic pressure, so hypertonic. So it is hypertonic. With respect to what? So with respect to red blood cell. Now what is, again, I guess now it is conversely valid. What will be hypotonic solution? If I have a red blood cell in a 0.8% saline solution, sir, here solute is less, so solvent will be more. Solvent more, so solvent will flow inside the red blood cell and it will swell. And because swelling will take place, so biologically it is known as hemolysis, because after increasing volume the cell may get ruptured. So this rupturing is known as biologically hemolysis. I hope everybody is clear with this. Acha, when just Abhilash, just after, I mean, just with another 5 minutes, I'll be starting electro. So I hope everybody is clear with hemolysis also. Now, moving to the last topic of solution and colligative properties, which is the correction factor. Sir, because we know, this shows how much good. Okay, thank you, Phantom. Now, beta, what is this Van 't Hoff factor? Because we know all the colligative properties depend upon the amount of solute present in the solution, and sir, it do not depend upon the nature. It is only worried about what is the number of solute present. So for example, if I have a solute which is having a property of dissociation, for example, let's say if I have NaCl and I have added 100 molecules of NaCl in my solution, so I will think that what is the amount of solute? 100. But sir, because this is getting ionized, so it will dissociate and form Na plus and Cl minus ion. And colligative property has nothing to do with nature. It is not worried you are NaCl or you are these. I am not depending upon your nature. I am depending only upon your number. So this 100 will form 100 sodium ions and 100 Cl minus ions. So actually the property will be experimentally calculated as per there are 100 solute particles, but theoretically what we will feel that it must be 100. That's why all the time when we were applying the formulas of colligative property, experimental value and our calculation, our theoretical calculated value were different. So that needs to be corrected. And it was corrected by observing this case of dissociation, and sometimes some solutes can associate also. Sir, give us an example of associating solute. The famous example, the only example of associating molecules are carboxylic acid. Why? Let's say if you have carboxylic acid, then sir, carboxylic acid will definitely, you can't stop carboxylic acid from having hydrogen bonding. Sir, why hydrogen bonding? Let me make that beautiful picture for you so that you can easily understand by yourself. So this is plus, this is minus, and this is minus. This is plus, this is minus, and this is carbonyl minus. And obviously this minus plus will attract each other. So for carboxylic acid, we have seen, for carboxylic acid per se, we have seen that if we have mixed 100 molecules of carboxylic acid, then after dimerizing, why? Because two molecules will behave as one. Colligative property has nothing to do with your nature, whether you are one, whatever you are. What is your count? So if I've added 100, they will dimerize and will practically give the count of 50. So sir, again, the experimental value and the theoretical value will come out to be different. So this was corrected by whom? This was corrected by Van't Hoff, and the Van't Hoff factor is written as I, which is nothing but whatever colligative property you are actually measuring as in experimentally measuring. So this is experimental colligative property upon theoretical colligative properties. Now, generally colligative properties that we practically, these colligative property determination we do because we need to find the molar mass of solute. Why? Because the colligative property is dependent upon concentration terms, molality, or either molarity or either moles. Sir, moles is equal to weight of solute upon molar mass. So if you have similar weight of solute, then colligative property is nothing but, sir, all the colligative properties are inversely proportional to molar mass of solute. So actually we are interested in the values of colligative property because we want to determine the molar mass of solute. So again, sir, if we have started experimentally seeing the molar mass of solute, then if we know the solute, then the molar mass that will be coming out experimentally, it will be abnormal. So what is the molar mass that you are expecting out of it? Your theoretical value. That's why this theoretical colligative property is also sometimes termed as normal colligative property, and the experimental value sometimes surprises you because you were not considering case of association and dissociation. So it is also sometimes theoretically termed as abnormal value. And because colligative properties are inversely proportional to molar mass, so I can also be written as molar mass normal upon molar mass abnormal. This is normal and that is abnormal. Now sir, that means that this is the actual value of colligative property and this is the theoretical value of colligative. Sir, theoretical value of colligative properties we have already derived. What are those? So then that means the actual value of elevation in boiling point will be I times of theoretical value. Actual value of depression in freezing point will be I times of theoretical value. So let me write the corrected formula of colligative properties then. Then means, sir, elevation in boiling point will be I times of the calculated formula. What is the formula? Sir, formula is Kb into molality. So this will be your actual value and this is my calculated formula. This is the corrected formula for boiling point elevation. So corrected formula for freezing point depression will be I into Kf into molality. Corrected formula for osmotic pressure will be equal to I into CRT. But the corrected formula for relative lowering of vapor pressure, because relative lowering is P naught minus Ps upon P naught. It is equal to number of moles of solute upon number of moles of solvent plus number of moles of solute. And because who is only getting the factor of dissociation and association is a solute, not solvent. So precisely it should be I over here. Yes, approximately we know colligative properties is valid for dilute solution. So N1 is obviously much larger than N2. So actually this is nothing but N1 only, but still you should know that it should be this for some good type of questions. I hope everybody is clear with this. Chalo. Are not visible only. Perfect. Chalo. Perfect. No worries. I hope everybody is clear till here. Now, after this, now let us define this. Let us derive the, okay. Actually, instead of that derivation, you should just, we do that derivation inside the class, but I feel you should, for your one shot summarization, you should just remember the case of dissociation value of I. So I for case of dissociation is calculated as 1 plus n minus 1 times of alpha. What is n, sir? Here NaCl dissociating into Na plus and Cl minus ions. So this one molecule is producing how many ions? 2. So here n will be 2. What is alpha, sir? Degree of dissociation. Generally, alpha is not given in the question. For what? For salts. And because salt is an ionic compound, so for them, alpha will generally be 1 only. If not, question will give you the value of alpha. What about dimerization, sir? Value of I can be calculated as 1 plus 1 upon n minus 1 times of beta. This beta is degree of association. If not given, take it 100%, so it will be 1. And n means if it is dimerizing, like acetic acid is dimerizing, so you do not have to worry. You just put that n as 2. If it is trimerizing, you do not have to worry. Just put n as 3. So on. I hope everybody is clear now. Similarly, these are some homework questions for you. The same questions, the same formula which I have done, just put the values and you will be getting your answers. Sir, are you giving us so many questions to practice? Yes. Last topic for solution and colligative properties, solubility of gas in liquid. Now, what is gas? Sir, we have discussed liquid in liquid solution. Sir, we have discussed solid in liquid solution. So the only thing remaining is gas in liquid solution. What is gas in liquid solution governed by? It is governed by Henry's law. Sir, Henry's law is a common sense. What is this common sense? You have seen from your childhood your cold drink. Cold drink is filled till here. The upper portion is kept vacant. Why? Because you want your cold drink to have that fizz of CO2. So if CO2 is dissolved in your cold drink, in your soda water, then obviously the pressure of CO2 has to be maintained above the solution only. Once you open this bottle and this CO2 is gone, and once you close this, now if the next day you are going to drink that cold drink, it will not feel the fizz. Why? This is nothing but solubility of gas in liquid solution, which says that partial pressure of gas, now this is the partial pressure of gas over the solution, is directly proportional to amount of gas that is dissolved inside the solution. This was statistically derived by Henry, statistically formulated by Henry, and therefore the proportionality constant is also termed as Henry law constant. And what is the concentration term that Henry has used to quantify the amount of solute of gas dissolved in solution? It was mole fraction of gas. So this is number of moles of gas dissolved in your solution. So it's if number of moles of gas in the solution is Mg, if number of moles of, let's say this is water, is number of moles of solvent. So what will be mole fraction of this? So it will be number of moles of gas upon number of moles of gas plus number of moles of water. And obviously for mathematical calculation, you should common sense it is, colligative property is valid for dilute solution, although this is not nothing colligative. But you tell me, if your cold drink is not having any soda, if is not having any fizz, will you able to just hold it and by weight you can say? No, sir. That means the weight of gas is nothing in present or in comparison to weight of water. So for mathematical ease, you can obviously write this denominator as number of moles of solvent only. Now, sir, what is this KH? Beta, this KH, unlike the value of delta TB and delta TF, there the value of K was property of solvent. This K is property of gas. As you change gas, value of K will change. And if you want to compare two gases, who is more soluble, who is less soluble, obviously you will make their partial pressure same. So this will be same. So K will be proportional to X, as K will be inversely proportional to X. So the gas which is more soluble will have less value of K, and the gas which is less soluble will have more value of K. So by just observing the value of K, you can comment upon the solubility of gas in the liquid solution. I hope everybody is clear with this. Similarly, you get some questions from Henry law also, and with this, I'm giving you these factors also. Some questions also are there. But yes, with this, we are done. We are done with solution and colligative properties, and I guess this is 9:33. So let us take a break. And we'll be meeting at 9:45 because I have to change the slides also, because I have to bring electrochemistry after this. So let us meet at 9:45 p.m. and then we'll be starting with electro. Cool. Now, all the students who are waiting for electro beta, we'll be meeting at 9:45 again. So 5 minutes, allow me to just change the slides, and we'll be meeting at 9:45. Okay, chalo. So come back. I mean, I already have very uh, limited crowd, but no worries, no worries. People will be watching us in the recorded version, so no worries. But yes, 9:45. Okay, chalo, bye. Yes, guys, I'm back. So, all the participants, I hope I'm clearly visible and audible again. So, whoever is here, just hit the comment section with a yes if I'm completely visible and audible, everybody. Come on, come on, guys. Am I visible and audible, everybody? Chalo. So, let's make it quick. I mean, why I'm saying quick? I'll be justifying the concept. Yes, yes, Abram. So I'll be definitely justifying for all the students who may be watching this anytime. So if you watch this, the backlog of electrochemistry is definitely going to be covered. Yes. So Ankit, Ganguly, and we have Abram. Chalo beta, let's start. Sir, for electrochemistry, the first and the foremost important topic of electrochemistry is the principles and the calculations around the batteries. Batteries are electrochemical cell which, because of a spontaneous chemical change, they produce electricity. And because they produce electricity, so sir, we have to know that how this battery can create current, sir. First of all, you need to know you need to know what is an electrode. So let us define an anode first. Let's say I have a bucket. I use water because I need ions, but sir, water has no ions. Water is very much less. Water is not even an electrolyte, sir. Yes, it partially dissociates into H plus and OH minus ion, but those H plus and OH minus ion are very limited. They cannot be used to conduct because, sir, the H plus and OH minus ion are very limited. So we have to add ions. Okay, so let me add some ions. Let's say I have a metal in aqueous condition in form of its ionic species. So this Mn plus is the ion which I've introduced by using a salt. Okay, now if I dip a rod of the same metal in this solution, then as this solid metal is dipped in this solution, what will happen? Sir, the equilibrium will get changed, the physical equilibrium and even the ionic equilibrium. Sir, how? This solid metal may disturb the equilibrium of the aqueous metal ions. In what sense? Sir, if it can have two properties. It can either ionize or it can get deionized, as in, if it is getting ionized, it will create ion and will create extra electrons. So the metal will be, let's say I was having 100 ions of Mn plus 2. I will be getting one extra ion of Mn plus 2. If this is happening and again equilibrium is reaching, and that will create electrons over here. Why I'm saying it is anode? Because this is nothing but the process of oxidation. Sir, but the opposite thing can also take place because equilibrium is disturbed. It can regain equilibrium after going ionizing also or after deionizing also. So let's say if opposite thing is happening, then sir, reduction will take place, as in you will have the same solution. But let's say here I'm adding some X plus N ions, and that metal X is deposited over here, then these ions may have the opposite tendency, as in these ions may take electrons and undergo reduction and can be solidified. So the, let's say I was having 100 of these ions. Out of these 100, one X plus will move towards this metal and will start to deposit. Sir, that means what is happening over here? That means this M plus, this cation is accumulating here. That means, sir, it must have gained the electron, so it will become, the outside environment will become negatively charged. Why negatively charged? Suppose I have copper sulfate solution. That means I'll be having copper plus 2 ions. Now out of those 100 Cu plus 2 and 100 sulfate ion, this was neutral. But once this 1 Cu plus 2 has deposited, the concentration of sulfate ion is now 100 and concentration of Cu plus 2 is 99. So this outside environment will become negatively charged, and the moment this will happening again and again, the minus will be accumulated outside and plus will be accumulated inside. Sir, do you find a picture over here? Sir, this picture is the picture of a capacitance. This picture is the picture of your basic physics capacitance. Sir, what is a capacitor? Which has a capacity to store charge. So if I have one capacitor electrically connected with another capacitor, and if I connect them with an electrical wire, then because they will have some potential difference, because this is another metal dipped in its own solution. So whenever a metal is dipped in its own solution, it acquires a potential. That potential is known as electrode potential. And once you mix two different potential, mix as in electrically connect two different potential, then the potential which is higher will give current. Sir, explain us this with an example. The very famous example of zinc and copper electrochemical cell. So here this is an anode, here this is a cathode. Let me give you the precise example of zinc and copper, because this is a very famous example. I guess you know it from class 9th and 10th. Sir, whenever zinc and copper are electrically connected through a metallic wire and you have a voltmeter in between, you find a electric current. Why? Because there is potential difference. Sir, from where electron is coming? Zinc is acting as an anode. That means electrons will flow from zinc. Sir, because zinc will be accumulating electrons, so electron will flow from here. And copper from the solution will come up and will accept these electrons and start to get deposit, and zinc will start to get dissolve. Sir, because direction of flow of electron is this, that means current is flowing in this direction. That means current is originating from the terminal which is acting as a cathode, where reduction is taking place. And that's why IUPAC has given a convention for these electrochemical cell, that the cathode, because current is originating from cathode, so at cathode what is happening? Reduction. So IUPAC said from now we will define electrode potential as reduction potential. If your question is asking electrode potential, you always refer that electrode potential as reduction potential. But sir, the charge carrier are current over here, but sir, circuit is not closed. No matter, don't close the circuit, still you are getting current. Yes sir, we are getting current. But beta, as zinc will start coming in the anodic compartment, the positive charge will keep on increasing in the solution. As positive charge keep on increasing, the concentration of Zn plus 2 ion will shift this equilibrium in backward direction, and the process will start to decrease. Therefore, the cell will soon die down. Moreover, the potential is saying that this is the higher potential and this is the lower potential. Once I have plus accumulating over here, similarly as copper is going, minus will start accumulating in the anodic compartment. So this plus minus polarity and that plus minus polarity will also oppose the current also. So soon enough this battery current is going to die down. Now I want this battery to work, because your battery that you buy from your market, it works till the end, till the battery is completely, till the reaction is completely done. When this reaction will completely done, when all the zinc will be dissolved. Dissolved is the physical phenomena which you will see. Practically what is happening, it is getting oxidized. So zinc, okay, the reaction is written, the reaction is wrong over here. It should be oxidation. So zinc solid giving Zn plus 2 and 2 electrons. This is the oxidation half, and reduction is perfectly written over here. So sir, zinc the cell will die when all the zinc will be will be dissolved. So this will be having nothing over here and all the copper will be deposited. But sir, this will only happen once you will negate this charge, the opposite charge that is being created over here, that will oppose the external potential, the external current that is created. So in order to complete the circuit as well and neutralize the charges formed, we introduce a inverted U-shaped tube called the salt bridge. Now in the salt bridge, what we do, we put a solidified electrolyte. Why? Because if it will be a liquid, it will be just flowing down due to gravity. So we solidify it by boiling it with a substance called agar agar, and then after cooling to a jelly-like substance, we fill the salt bridge with the inert electrolyte. Why inert? Because it should not react. It is used. Why? The as soon as Zn plus 2 extra cations are creating over here, the negative charge from the salt bridge will rush towards the positive and will neutralize the extra positive created. Similarly, as soon as copper has gone, sulfate has increased, so negative charge as start building up, the cation will rush towards this side and will neutralize the extra ion created, thereby neutralizing the charge. So what is this function of salt bridge? The function of salt bridge is to maintain electrical neutrality in the cathodic and the anodic compartment. I hope everybody is clear with this. Why this is U, beta? I mean, obviously you need to have access on that side also and this side also, and there you need to have some stuff. So the structure is anyway U, so that's why a U-shaped tube. Because if you have let's say you have a V-shaped tube, then in that V it will create a gradient, so that U-shaped tube will also not create a gradient, because obviously these cations also have to move. So what type of cations I will be using, which will be having same ionic mobility? So technically it is termed as the transport number. So the transport number of the cations and anions should also be same. So what type of electrolyte we should use? One, we should have same type of cationic and anionic mobilities. Two, those cations and anions should not start reacting, because if they start reacting, they will form a PPT. Once they will form a PPT, this opening, this enclosure will be getting sealed, and again the cell will stop to function. So you do not want them to react. Point number one. You want their ionic mobility of the ions used in the salt bridge to be same. And last but the most important thing is why their ionic mobility should again be equal, because if K plus is moving fast and Cl minus is moving slow, then this, let's say this has been neutralized, but this is taking time, so that will also create a energy loss, which is quantified as liquid junction potential. So in this junction of this liquid and the gelatinous jelly-like solid, although because ions are free to move, so that is also a movable solid. That is why it is called a gelatinous solid. So at this junction, the speed with which cation should approach will be same, should be same with which anion should approach the other end. Why? Else one will neutralize, another will not neutralize. So again it will create a doubly layer. So what is that doubly layer? So this is plus and this is minus. This plus and this minus has opposite polarity of this plus and minus. So here current is like this, so it will also create a current in the opposite direction. So this is called liquid junction potential, which has to be avoided. Why? Because it is opposing the output current. That means the efficiency of the cell. So this is the liquid junction potential, and if you want your cell to be highly efficient, then liquid junction potential has to be 0. This constitutes your electrochemical cell. Now, sir, how will I calculate the electrode potential? Because this voltmeter will always read the difference of potential. Yes. And what difference are high minus low? What is higher potential? Sir, cathodic compartment. Therefore, the cell potential will be it is just KVL, KCL of your physics, but I am just writing the final conclusion. The difference of the two potential. That means higher potential as in electrode potential of cathode minus electrode potential of anode. Now why I'm saying electrode potential? Because what potential I'm comparing? The reduction potential. Why? Because we have summarized and identified and defined this, that as per IUPAC, although this is getting oxidized, but why this is getting oxidized? Because that cathode has higher potential to undergo reduction. So what potential we compare for two species? We compare their reduction potential, and that's why what value we are going to put over here? Reduction potential. So the cell potential for this Daniell cell will be the reduction potential for cathode. Whose cathode? Copper. So reduction as in copper plus 2 to copper value we'll be putting over here, minus the reduction potential for anode. Although this is getting oxidized because it is having less reduction potential, so that reduction potential is Zn plus 2 to Zn. I hope everybody is clear. Now, sir, okay, that U-shaped tube I already answered because I don't want any gradient to be created, beta. Sir, why not use resistor? Beta, this I'm using for what? Practically, if you do not use the salt bridge, practically, yes, practically, if you do not use the salt bridge, do you get current? Yes, you will get current. But soon enough, what will happen? As the concentration of zinc ion will increase over here, the concentration of product will increase and it will force the equilibrium in backward direction. So, sir, oxidation will be happening in a lesser amount. The amount will keep on getting lesser and lesser as the concentration will keep on growing. So soon the cell will stop to give a current. Point number one. Point number two, if the circuit, if you're just watching the circuit, this is positive terminal, this is negative terminal. So current flow is like this. As the positive charge here and negative charge here will develop, it will create a double layer, this plus and this minus. So this potential will be opposing the potential of the output battery. So I want these charges to be neutralized as they are formed. So the reason we are using salt bridge is to neutralize the extra charge created, and because I want the ions to move towards those respective electrodes, and therefore I want their speed to be same. That's why I'm using a U-shaped tube. I hope everybody is getting it. I hope everybody is getting it. So Appy, Appy. I hope Appy is saying repeat the last page. This is the, so what was the construction I had? I had a anode half. Sir, anode was having extra electron, so it will give electron. Cathode was having deficiency of electron, so it will receive electron. So current will be coming out from cathode and moving towards anode. That completes your electrochemical cell. That completes your electrochemical cell. Now, this is the cell potential. Sir, but how we will experimentally calculate electrode potential of cathodic and anodic compartment? Because I will always, through the voltmeter, I will always see the difference between two potentials. So that's why we have started calculating this in a standard condition. What is that standard condition? Standard condition is once the temperature of the environment in which this reaction is allowed to take place is room temperature. Technically standard value is 25 degrees Celsius. Once the concentration of the ions, because as concentration will change, the value of their extent to undergo oxidation and reduction will also change, because ultimately the concentration is deciding that reaction is going in which direction. Because for every metal ion with respect to temperature, there will exist an equilibrium constant K for their existence in solution. So once you introduce a rod into its own solution, the value of at the real time, the value of Q will be happening, and Q once compared with the value of K will decide that forward reaction will take place or backward. And once equilibrium will be reached, cell will cease to function. Cell will stop giving you potential. So therefore, what is the temperature that on standard condition it is chosen? Standard temperature is 25 degrees Celsius, and standard pressure of the environment, you will also see gaseous electrodes, is 1 bar, and the concentration of ions is 1 molar. During that condition, whatever potential we measure is called the standard potential, and it is written with a symbol not. So this represents the standard value, and the above cell represents the any general value. Now, so still, how will we calculate the electrode potential? So for that we need a reference, because that reference I will mark as 0. Therefore, sir, this voltmeter will always read the potential difference. But if we assign the potential of a particular electrode as 0, then that will become 0. Then the potential value will be giving me the value of that particular electrode potential. So what is this reference electrode that we choose? What is this reference electrode? Now these all junction potential I've spoken about. Let me directly what is the reference that we choose? We choose hydrogen as the reference electrode. Sir, but hydrogen is not a metal. How will we dip hydrogen electrode into its own solution? Now that's a common sense. What is that common sense, sir? You just create a bucket, put water, add H plus ions, because it is standard condition, so make H plus ion concentration as 1 molar. Now you need a inert metal. Sir, why inert metal? Because inert metal will just make available its metallic surface for the reaction, and metallic surface will allow the flow of electrons. So this becomes your inert electrode, which is generally platinum. We coat this platinum with platinum black, because what is platinum black? The same platinum crushed and pasted over the platinum metal, because the crushed area will give the platinum surface a more surface area. More be the surface area, so more gas can be adsorbed on the surface, and therefore much larger reaction extent can be observed. Sir, but this is your platinum inert metal. Okay, sir. So this platinum solid will act as your inert metal, and into this platinum solid we pass hydrogen gas. What hydrogen gas will do? It will start to get deposited. What is the process known as adsorption? So it will start to it'll start to get adsorbed on the metallic surface. So sir, although this is platinum, but chemically it is what? Sir, chemically it is hydrogen gas interacting with H plus ions. So hydrogen gas interacting with H plus ion can again create an electrode potential. How, sir? What potential we assume as electrode potential? Sir, reduction potential. So write the reduction half reaction. Sir, H plus gaining those electrons and forming hydrogen gas. Sir, this is aqueous ions. So sir, this can take place. Yes, the potential will be, sir, from H plus to H2. Sir, this is the reduction potential, so it will be termed as electrode potential. Because I'm taking standard condition, so you can write as E naught of this hydrogen electrode. This is nothing but standard reduction potential. I am not saying it is 0. It will have some value, but as per IUPAC, we choose it as a reference. Therefore, we assign it to be 0. I am not saying this potential is 0, but we assign this potential as 0. Why? Because if I use this hydrogen electrode in front of, zinc, if I use hydrogen electrode in front of zinc, then the potential that I will be measuring will be giving potential of that minus this, because that is 0. So whatever voltmeter will be reading will be the potential of the another electrode. So what potential we measure? Sir, we measure the standard potential, and this standard electrode is termed as the reference electrode, which is nothing but the standard hydrogen electrode, which will help us to calculate experimentally the electrode potential of all the available electrodes in practical life. So that means the electrochemistry division must have done this. Yes, they did. And after doing that stuff, they have created a series. That series is known as electrochemical series. That series is known as electrochemical series, in which this is the reference hydrogen whose potential is assigned as 0. I'm not saying it is 0, it is assigned as 0. And once with respect to hydrogen taken as 0, the standard value, if you calculate the electrode potential of all the electrodes and arrange them in increasing order, then this is the series that you get. Sir, do we have to remember this series? No, beta. For mains level of question, generally the value of electrode potential is given. For advanced and for inorganic type of questions, yes, sometimes you have to remember them. There is a rhyme, but the percentage of that coming is very less. And yes, we do some Faraday law of electrolysis, the qualitative and quantitative analysis, and during that analysis, I will give you some trick. But for just for the question of electrochemical cells, rather value of standard potentials are always given. So do not learn this, but yes, you can obviously see this, that metals are coming at the top. That means they are having least value of reduction potential. Obviously they are metals, so they want to get oxidized. Why will they will never want to get reduced? Therefore the electrode potential of these metals are negative. That means they do not want to undergo reduction. That means they want to get oxidized. So what we generalize by seeing this electrochemical series is, if electrochemical series is arranged in the order of increasing value of electrode potential, standard electrode potential I am representing as E0, this standard electrode potential is increasing. So whoever is coming at the top do not want to get reduced. That means they want to get oxidized. The electrode at which oxidation takes place is termed as anode. So whoever is coming at the top will become the anode, and whoever is coming at the bottom, I'm not saying below hydrogen. Let's say if I compare these two, because calcium is coming at the top, so it will behave as anode. Sodium is coming at the beneath calcium, so it will behave as cathode. So this is the application of electrochemical series, by which you can choose that which electrode can act as anode and which electrode can act as cathode. Again, a theoretical redox thing that is mostly asked in your JEE mains and maybe advanced paper is, sir, because the electrode who is coming up is willing to get oxidized. So if I myself get oxidized, I will reduce you. So what I will be termed as? I will be termed as a strongest reducing agent. So whoever is at the top is the strongest reducing agent. Vice versa, whoever is at the bottom will be acting as strongest oxidizing agent. These questions are very much asked. These questions are very much asked. I hope everybody is clear. Chalo. Now, sir, for metals we know this. Okay, for metals we know this. But yes, for sir, then we can formulate that electrochemical cell for ions also, and those ions, for negative ions also we can do it. Yes. So negative ions, sir, will do what? Sir, negative ions will get oxidized. So they will be discharged where? They will be discharged at anode once you use them for your electrolytic cells. So this is a famous order. Therefore, you should learn this. That who has higher capacity to undergo oxidation, sir, you said you do not have to read the value, but these are only for metals. Your NCERT has for metals also, for anions also. So I'm not asking you to learn the value, but learn this trend. For what is the order of getting discharged at anode, as in what is the order of them getting oxidized? Sulfate has got the least tendency. It is one of the famous ion. More than sulfate, hydroxide ion has a capacity to undergo oxidation, then Cl minus ion, then Br minus ion, then I minus, and obviously strongest will be F minus. So just for these anions you should learn that what is their tendency to get oxidized. So obviously I minus will oxidize and form I2, Br minus will oxidize and form Br2. So if two ions are compared, then who will win for oxidation, for getting oxidized, that is who will be give the product of electrolysis at anode, sir, these. So I mean, yes, they are more famous for electrolysis side of chemistry, so you can leave them for time being, because yes, we will be discussing again, for their discussion will be again done for the product of electrolysis, but yes, later. But that is also based on the value of electrode potential. I hope everybody is clear. Yes, Silver Boy, hello. Sir, when will you do mole concept in backlog series? Beta, mole concept, the previous live I have done, no, it was more of concentration terms. So there I have done the mole concept that is required for class 12th chemistry. Hai na? Then we have Jagruti. Okay, Jagruti is wishing me. Thank you, Jagruti. Chalo. Sir, what is EA and EC? Beta, EA represents electrode potential of anode, IATN, and EC represents electrode potential of cathode. If you write a not in their superscript, then that will become the standard potential of cathode and standard potential of anode. Okay, IATN. Chalo. Now, sir, this electrochemical series, that means we can make use also. You can have some practical inorganic relevance also. Yes. समझ आ गया, perfect, धन्यवाद sir. Okay, now moving forward, now I'm not done yet. Now sir, that means you have said that these are the standard values. So if we change the concentration of ions, or rather if we change the temperature, then whole equilibrium thing will change. So the changing temperature and concentration of ion will change the value of electrode potential, yes, and that will be the general electrode potential, which IITN has written. EA and EC are the electrode potential of anode and electrode potential of cathode at any general time t, when you do not know what is the concentration of ion, when you do not know what is the temperature. Then sir, how will we calculate the electrode potential? In order to calculate electrode potential, what we have is, we have Nernst equation. Now Nernst equation helps us to quantify, Nernst equation helps us to quantify that how changing concentration and temperature will change the electrode potential. How does it do it? Let me directly jump to a question and tell you about Nernst equation. See, a very basic, a very famous question, and obviously discussing about Nernst equation only. So let us solve this question and try to understand how you apply this Nernst equation. So we directly apply this Nernst equation with a mains question and we learn it also. Now, here you are given a cell, but sir, I cannot see that cathode, anode, dipped. Sir, what is this? This is the cell representation. Obviously, in your questions, they will not give you the complete picture. Rather, they have a technical feature which is called cell representation. What is the cell representation? You have a salt bridge represented by a double dash. On the left side, you have anodic compartment. On the right side, you have cathodic compartment. That is, who is getting oxidized? Copper. Who is getting reduced? Silver. But now the concentration of copper ion is not 1 molar. So it is not standard condition. It is some value. This silver plus ion is also having some concentration, which is definitely written. This is how you represent a cell. Now, sir, that means, sir, at least by watching this first cell, I can say copper is anode, so oxidation must be taking place. So what will be anode half reaction? Copper solid forming copper plus 2 aqueous and giving 2 electrons. Okay, sir. What is acting as cathode? Sir, zinc, silver. Sir, silver plus ions from the solution must be taking those electrons and getting deposited as silver solid. So this is anode half reaction and this is cathode half reaction. How will you write the complete cell reaction? Sir, add them. Sir, how to add them? You have to make the charge transfer equal. How to make the charge transfer equal? Sir, this one guy is giving 2 electrons, so I need 2 electrons here also. So multiply this equation by 2 and add them. So what will be the overall cell reaction? Copper solid plus twice of Ag plus aqueous is giving copper plus 2 aqueous plus twice of silver solid. Why I'm intentionally writing solid and not writing aqueous? Because iron, you know, it is in aqueous medium. Because iron, hi sir, okay, hello beta. Umang is saying hi and then bye. Okay beta. Now, copper is getting oxidized and silver is getting reduced. And why I'm focusing on writing the solid? Because we know pure solid and pure liquid do not impact the state of equilibrium. Then who does? Sir, gaseous species and ions. So how can you write the equilibrium constant for this reaction? Sir, not equilibrium constant, because at any variable time t it will be reaction quotient. So what will be the reaction quotient of the cell? So this Q will be concentration of product, but only of the ion. So who is the product? Sir, copper plus 2 concentration raised to the power 1, because stoichiometry is 1, upon silver ion concentration, sir, raised to the power 2, because stoichiometry is 2. So this is the value of the concentration that will impact the value of electrode potential. Now, what we are trying to calculate over here, sir, cell potential. So how can you calculate cell potential, sir? You already told us. Sir, cell potential is equal to cell potential of electrode potential of cathode minus electrode potential of anode. We know this, sir. According to Nernst equation, what you know? According to Nernst equation, we know that cell potential or electrode potential is equal to standard cell potential or electrode potential minus RT upon NF into ln of the reaction quotient Q. If it is an electrode, then you write the Q for the electrode half reaction, and if we are doing it for the complete cell, then the trend goes the same. That is, electrode potential is equal to standard electrode potential minus RT upon NF into ln of Q. Now, R is universal gas constant, so value will be 8.314. T, because 8.314 is the value in SI unit, so we use 8.314. T, sir, generally the question that is given to us is at 25 degrees Celsius. That means it will be 298 Kelvin. N is number of electron transferred, which will be 2 in this particular case. Yes, it will change for all the type of reactions, but in this case it is 2. F is charge on 1 mole of electron, which is 96500. Exactly, approximately it is 96500. Exactly it is 96487. If you convert ln into log, you will get a multiplier 2.303. So what we do for calculation, we learn the conclusive multiplier. So after putting all the data that is generally taken as constant, we can say that this cell potential, which I do not know because this is not concentration, this is standard, this is some general condition. So it will be equal to standard cell potential, that is when that you can get from the data sheet. So E naught cell minus this constant, all these constants can be written as 0.0591 upon number of electron transfer becomes the only variable, and because I have multiplied 2.303 also, and you should learn this because this is mathematically very useful, so this ln becomes log Q. Now applying this for the given question, sir, cell potential is given here, which is 0.3095. It will be equal to E naught cell, which will be E naught of silver cathode minus E naught of copper, although E naught of these electrodes are not given. But because E cell is given, and as per Nernst equation, E cell is equal to E naught cell minus 0.0591 upon number of electron transferred is 2 into log of. Now the concentration are also given. What is concentration of copper ion, sir? 10 raised to power minus 1. What is concentration of silver ion, sir? 10 raised to power minus 2, but I have to square it, so it will become 10 raised to power minus 4. So it will become 10 raised to power 3, so it will be 3 log 10. So this will be nothing but 3 log 10. 3 into log 10 is 1. Now I hope you can solve this, and once you solve this, what you will get, sir? You will get the value of E naught cell. What to do with this value of E naught cell? At least we knew Nernst equation also, and we have applied a question also. Now, sir, now after this, sir, from the first half we have calculated E naught cell. Okay, sir. Now the second half is telling us that for cell this, you now calculate cell potential. Then, sir, again apply Nernst equation. Why? Because now we know E naught cell. We have to calculate E cell for this new reaction. And why it is new? Sir, cathode anode are same. No, concentration is getting changed. So here concentration is not 10 to the power minus 1, it is 10 to the power minus 2. Here it is not 10 to the power minus 2, it is 10 to the power minus 3. So use again that. Now you know E naught cell, and once you solve this, I am giving you answer also. It will be 28. It will be 28. So it'll the value, I mean, once you solve, it will be coming out to be 0.28. So because you have to represent in a sign, in a note, in a format like dash into 10 to the power minus 2, so it will be 28 into 10 to the power minus 10 to the power minus 2. I hope, beta, these type of questions are very, very, very prominent in your mains examination. I hope you are done with Nernst equation. Now, quickly moving to concentration cells. What are these concentration cells? Sir, you have already told us that how to apply Nernst equation. You have already told us that cell potential and standard cell potential is the difference of electrode potential of cathode and anode. But sir, once we have the same electrode, then can we change the concentration? Yes. For example, concentration cell are of two types. One is electrolytic concentration cell. What is an electrolytic concentration cell? Suppose, let's say I have an example also. Acha, this is a good one. Chalo, let me first give you basic. Okay, what is electrolytic concentration? Let me represent the cell, rather not draw it. Let's say I have zinc solid getting oxidized to Zn+2, but concentration is C1, salt bridge. In the cathodic half also, I have zinc ions with concentration C2 getting reduced to zinc solid. Huh? Sir, you have already told us as per Nernst equation, if you change concentration, potential can change. So this is potential V1, this is potential V2. If you join two potential difference, you will find current. Write Nernst equation for this. So if I write Nernst equation for this, then I will say the cell potential will be equal to standard cell potential. What will be standard cell potential? Sir, it will be E0 cathode, which is again copper, which is again zinc, minus E0 anode, which is again zinc, although value is not given, but because I know both are same terminal, therefore what is the E0 cell value? Sir, it will be 0. So what is concentration cell? When E0 cell is 0. How it can be 0? I hope I explained you that. So that means cell potential is equal to standard cell potential, which is 0 because it is concentration cell, and such a cell is known as concentration cell when you have same terminals, minus 0.059 upon number of electron transferred, in this case is 2, into log of, I hope now you know, you will write this reaction. So zinc ions will be coming in the product, zinc ions of what? Of the anodic compartment. Stoichiometry will be 1. So concentration of zinc ion from the anode upon concentration of zinc ion from the cathode. So if you want this now, if you want any cell to function, you will want it to have a positive voltage. So sir, E cell has to be positive. So for making this E cell positive, that means cell will be feasible. So this has to be positive. But sir, I have this negative sign because this is already 0. So this log value has to be negative. That means value of this x, log of x is negative and x is less than 1. That means C1 upon C2 has to be less than 1. That means concentration of the zinc ions in the anodic compartment has to be less, and on the cathodic compartment has to be more, and then this concentration cell will definitely give you voltage. So this is your concentration cell. Yes, you can also have this concentration cell. This is an electrolytic concentration cell where I have changed the concentration of electrode of the ions. You can also change the concentration of the gas, because sir, for gaseous electrode it will be electrode happening deciding the reaction, and the more pressure of the gas you will use, the more and more the potential, relatively they will create the potential. So that will be known as electrode concentration cell. And yes, the only reason I have skipped this, because this is a good question, because this will be requiring the knowledge of ionic also. Like what? Who is anode? Sir, hydrogen gas getting oxidized to H+. Who is cathode? Sir, H+ ion getting reduced to hydrogen. So again, but this is what electrode? You can have electrolytic and electrode also. How? If I change the pressure of the gases also, let's say P1, P2, so it will be electrode change also, and here concentration is also changed. So you can have electrode concentration cell also and electrolytic concentration cell also. So what is the concentration? So what will be H plus ion concentration? It is given by strong acid. So whatever H plus, whatever concentration of will be of HCl, the same concentration will be of H plus ion, because sir, strong electrolyte will completely dissociate. So now the funda of ionic equilibrium will be applied for calculation of H plus ion concentration. What will be the H plus ion concentration of this weak acid? Sir, H plus ion concentration for weak acid is nothing but under root of the equilibrium constant of that, the dissociation constant of weak acid into the concentration. So, sir, value of Ka will be given for this weak acid in the question. Yes. So, how will you write? Let's say, let me write it. Let me just do it for one. So, what is getting oxidized? Hydrogen forming H plus and giving electron. But hydrogen from which compartment? Anodic compartment. Let's say this pressure is P1. Concentration of H plus ion, you can obviously see C1. Who is getting reduced? Sir, hydrogen is only getting reduced. So H plus ion from solution will take those electrons and form hydrogen gas. This hydrogen gas is pressure what? Let's say this pressure is different, pressure P2. So this concentration I have already calculated using ionic equilibrium. It will be K into concentration of this, which is weak acid, which is C2. Complete cell reaction will be, you can obviously see. So how to write Nernst equation? Sir, E cell will be equal to E naught cells, a standard potential of hydrogen here also, hydrogen here also. So E naught cell will be 0 minus 0.059 upon number of electron transferred is, sir, 2 into log of. Now I'm just writing Q by making you see the reaction. Just see the reaction, beta. Sir, here hydrogen gas will be on the product side, stoichiometry 1. So for gas, what you can write? The pressure of the gas. So what is pressure of the gas for this hydrogen? Sir, it is pressure P2 for the cathodic compartment. Pressure P1 for the anodic compartment. So pressure P2, this, sir, but I will have H plus ion concentration also in the product, raised to the power 2, because stoichiometry is 2. So for ion, what I write? Concentration of this is C1. So concentration C1 squared upon in the reactant side, hydrogen gas I have with pressure P1 raised to the power 1, because stoichiometry is 1, and H plus ion concentration is KaC2, but squared, so it will be just Ka into C2, because squared. So I have definitely given you a general. You can obviously use the common sense and apply this common sense for all type of concentration cell. So I hope you know what is a concentration cell as well. Okay, sir. Now moving to what? Now moving to the last part, sir. Last part of the important part of these electrochemical cells. Sir, the thermodynamics. The thermodynamics. Acha, you have types of electrodes also, but yes, I'm just leaving type of electrode slide right now because they are good. That is a good topic. So I want you to first revise these things with loads of questions. I'll be giving some homework questions also along with this. Sir, under root wala I didn't understand. Okay, let me just give you that, beta. Here. See, beta, how you will write Q for the concentration of product upon reactant. So for reactant, for gases, I'll be writing pressure. So pressure P1. What is stoichiometric coefficient of hydrogen? So P1 raised to the power 1. Okay, sir. Now, concentration of H plus ion raised to the power 2. What is concentration of H plus ion? Sir, it is for a weak acid, concentration of H plus ion will be approximately equal to under root of K into C2. This is ionic equilibrium, beta. I hope you remember that at least this much, that for weak acid, how you calculate H plus ion concentration? Under root of K into C. So because H plus ion concentration is this, so square of this is what? K into C. So K into C2, because concentration given for weak acid is C2. Akshat Sharma, did you get that, beta? Beta ji. Beta ji. Chalo. So now coming to the thermodynamics. Coming to the thermodynamics involving these electrochemical cells. You go away. Coming to the thermodynamics involving these electrochemical cells. Sir, I have just seen lecture 5 of Faisal sir from Lakshya. Okay, beta, very good. No worries, beta. I mean, you see anywhere. NCERT, beta. All the teachers who teach for JEE, they teach with what as reference? NCERT. Yes, definitely. You get a sync with the teacher. So yes, wherever you get the sync, do that. Okay, Akshat is saying clear, sir. Samarth is wishing me happy birthday. Thank you, beta. Chalo. Now let us finish this quickly. Hana. Now, so thermodynamics is very important. So let us learn that thermodynamics. Okay, sir. So thermodynamics says thermodynamics involving electrochemical cells says first one thing. Sir, I get all the concept. Perfect, Hardeep. Now, thermodynamics says few things. First thing, delta G as in Gibbs free energy change, which is useful work done by the cell. Sir, if any cell is spontaneously giving work, then delta G we know from thermodynamics will be negative. But negative what? NFE cell. Sir, how do you have to learn this formula? Beta, potential is equal to work done upon charge. Potential is equal to work done to move a charge. This is work. Sir, potential. Potential is equal to work done upon charge. What is the charge flown? Sir, one mole electron has charge F. So n moles will have NF. So this is charge into potential is your work. Useful work is this. Sir, in standard condition, second thing is from thermodynamics, I know delta G is equal to standard value of delta G plus RT ln Q. And we know, sir, at equilibrium, once you have reached equilibrium, that means at equilibrium cell will stop to function. Cell will not give any current. So at equilibrium cell you have to throw that current battery out because it has stopped working. That means it will give no useful work. That means reaction has reached equilibrium, so Q will be K. So use that in the above formula. You will be getting delta G naught, which is standard delta Gibbs free energy change, will be equal to minus RT into ln of K. So this is another form that you should know. Now, obviously, it can be written as 2.303 RT log K. Now, how can you relate this K and E cell? Sir, we also know that. What? Sir, we know E cell is equal to E naught cell minus RT upon NF into ln of K. And again, sir, at equilibrium, sir, if delta G is 0, then sir, cell will also not work. So E cell will also be 0. Okay, this is Q. And at Q will become K. So now you can relate E cell, E naught cell and log K also. So you can say this is 0. So E naught cell will be equal to, this will be coming with a positive sign, RT upon NF into ln of K. Or now you can, because this is very much used, use all that value. So it will be 0.059 upon N, and this ln becomes log K. So these are some direct thermodynamics formula which you be using, which you will be definitely using for your JEE mains and advanced questions. Again, you give me some tips to find log of any number, because sir, what ma'am has teaches us in school was so confusing that I can't understand anything in school. Yes, beta. Keshav, log is also, let me give you some log basics. Although I have given those log basics a lot of time in my classes, but chalo, dekho, the only thing you need is log of A into B is nothing but log A plus log B, first formula that you should know. Then log of A upon B is nothing but log of A minus B, that you should know. Then log of A to the power B is nothing but B times of log A, that you should know. And you should know the basic log, that if log of A to the base B is C, then this mathematically mean B raised to the power C is A. So if this you know, then along with these formula you can do your common sense. And one more thing, what is the graph of log? Graph of log is this. If this is log x and this is x axis, so this is x equal to 1. So if log x is greater than 1, then it is positive. If x is greater than 1, then log x is positive. If x is less than 1, then log x is negative. Now, in order to calculate value, you just need to learn the log of prime numbers. So log of 2, similarly log of prime numbers, 3. So log of 5, log of 7, And log of 10 is obviously a common sense, because what does log mean? Whenever we write log, it means to the base 10. Whenever in chemistry you see log, it means to the base 10. And whenever we mean log to the base e, we write ln. We don't write log. In chemistry, NCERT follows the trend, and therefore JEE, NTA, they follow the same trend in chemistry questions. That whenever they are writing log, even they are mentioning or not mentioning, that means they are making base as 10, this base. And whenever they are writing ln, they mean base is e. How to convert log, base e and base 10, that also let me write it. So ln of x is nothing but 2.303 times of log of x. And last thing is these values. So very easy, 0.3, then 0.5, 0.7, 0.84 and 1. If you learn these, just apply whatever value you have, just break down to a smallest value, fractionalize it in these prime numbers, and then you can obviously calculate using these log properties. But yes, for you need to practice beta. Anna? Yes, sir, this is clear. But that time, sir, when log of any number is asked, then how can I find it? Log of any number, okay. So see, just say for example, log of k, let's say log of k is anything. You solve it, let's say minus 26.5, whatever. You can approximate to 26.5 like this, Anna. So k will be equal to 10 raised to the power minus 26.5. Just go to the next integer. So 26 minus 27. So now you are having an integer, so it becomes a scientific notation. And what, sir, it will be somewhere around 0 to 1. So what is it? Minus 26, that means I have to add 0.5. So 10 is power 0 is 1, 10 is power 1 is 10, and 10 is power 0.5 is 3.162. At least learn under root of 10, this is 3.162. So this is how you can approximately get the ABCD options. So this is how you can use log. Okay. Chalo. Now. And this is redox. These type of cells also, this is a redox. Here, using platinum as inert electrode, this is getting oxidized, and using platinum as an inert electrode, this is getting reduced. So this is a type of electrode which is redox electrode, because no metal is used. No metal of the constituent exist. It is also taking help of an inert electrode. But that inert electrode is coated with a paste of Cr+3 that side. This inert electrode is coated with a paste of Sn+2 in this side. So obviously, how, sir? Again, apply Nernst equation. So first write the reaction. So Cr+3 is getting oxidized to Cr+6, giving 3 electrons. This is oxidation half. Sn+4 will be gaining 2 electron and forming Sn+2. This is reduction half. If you want to balance, then sir, charge transfer should be same. So multiply this reaction by 2, because 2 into 3. Multiply this by 3, because 3 into 2 is 6. Then add them. So it will be twice of Cr+3, thrice of Sn+4, giving twice of Cr+6, and thrice of Sn+2. What will be E cell? Sir, E cell will be equal to E naught cell. E naught cell will be E naught cathode. This is +3 to +6. Okay, no. What is electrode potential? Reduction potential. So this is +3 to +6. That means this is oxidation potential. So reduction potential will be minus A volt. This is reduction. So for tin it is B volt. So who is cathode? So tin is cathode. So tin is B volt. Minus E naught anode. So for anode, reduction potential is minus A. So minus of minus A is plus A. So this will be your value of E naught cell. So E cell is equal to E naught cell minus 0.059 upon number of electron transferred is 2 into 3 is 6 into log of. Now write Q, those coefficients you have. So concentration of Cr+6 raised to the power 2, concentration of Sn+2 raised to the power 3, concentration of Cr+3 raised to the power 2, concentration of Sn+4 raised to the power 3. This is how you can write electrode potential. Perfect, Keshav. Perfect. Chalo. I hope everybody is clear till here. Now, what I was discussing, thermodynamics. How much thermodynamics we have discussed? Sir, we have discussed till, okay, now one more thing. Very important this thing. Beta, work is thermodynamically speaking, work is extensive. That means it depends upon amount. But potential is intensive. Why? Because potential is work upon charge. Both are extensive, so ratio of extensive is intensive, independent. So that's why, because work is extensive depending upon amount, so if you add reaction, work delta G will get added, but potential will not getting added. So how you can calculate potential using that phenomena? Beta, certain those questions are not important. They are super important. Sir, can you give us those questions? Yes, because they are super important. So obviously I'm giving you those like this. Okay, let us do this. This is a JEE Advanced question. Let us directly do a JEE Advanced question. Basic question, but yes, very much useful to understand this. The reduction potential of this is given. Sir, here manganese is in +7 state. Here it is +2. So it is +2 state. So I have to calculate reduction potential for this. As in, write the reaction. Sir, MnO4 minus forming Mn +2. So obviously I know 7 to 2, that means I'm not balancing the complete reaction, because I know it will be needing 5 electrons. It will gain 5 electron and come in +2 state, reduction potential. So for this, let's say for this reaction, let's say Gibbs free energy changes delta G1. Why I'm interested in Gibbs free energy and potential is asked because you can add reaction, delta G is work. It will get added because it is extensive. Potential will not. So sir, how will call? Let me tell you. So first write the delta G. Okay. Now what is given? Sir, from MnO4 minus to Mn +2, as in from +7 to +4 it is given. As in MnO4 minus, how many electrons it will gain? 7 to 4 is 3 electron it will gain, and it will form MnO2. I'm not balancing the complete reaction. Why? I'll tell you. Then what is given? Sir, for MnO2 +4 to +2, that means it will be taking 2 electrons and forming Mn +2. Potential is also given. So let's say this potential is A volt, this potential is B volt, and this potential is C volt. What is the reaction? Sir, Mn +2 taking 2 electrons and forming manganese. Now these are my 3 reactions. What are these 3 reactions? Having work, Gibbs free, and okay, because they are standard values. So let's say this is delta G01, this is delta G02, this is delta G03, and this is delta G04. Why I'm writing work? I'm telling you. You just see these reactions. What I can mathematically do with these reactions so that I can generate this one. Sir, I need MnO4 minus in the left hand side. So I need this in the left hand side. So take this first reaction. Add the second reaction, sir, MnO2 will be getting cancelled. Then add the third reaction also. Sir, Mn +2 will be getting cancelled, and I will just be getting manganese, and that is, acha, I will not be getting manganese. Okay, this is manganese only, beta. This is manganese only then. This is manganese. That was no misprint. This is manganese only. So from +7 to 0, that means. So I have to gain 7 electron, that means. Okay. So this is manganese. So this is also be getting cancelled, and I'll be getting manganese. So in order to get that reaction, I'm adding these 3 reactions. Potential can't be added, but work can be, because it is extensive. So I can say delta G01 is equal to delta G02 plus delta G03 plus delta G04. 4. I hope everybody is clear with this. Now we have already derived the formula. Delta G is equal to minus NFE, but delta G0 will be equal to minus NFE naught. E naught is given. So I'm not writing complete formula. Why? Because minus F will be getting cancelled. So do not think about that minus, because delta G0 is minus NFE naught. Minus and minus NF, minus F, everybody will be having. So minus F, minus F, minus F, minus F. Don't think about it. Then think about what? Sir, minus gone, cancelled among all, F gone. Then E into potential. So what is charge transfer in first case? Sir, 7. 7 into potential, sir, that potential I want, so X. What about second? Charge transfer is 3. Potential is, sir, A, you put the value, A volt, so 3A plus charge transfer is 2. Potential is B. Charge transfer is 3. Sorry, this is third reaction. That answer is 2 only. 2 na? Just check. Plus 2. Ah, ठीक, 2. So 2 and then see, put the value of A, B, C with sign. This is negative, just make sure. Put the value with sign, divide by 7, you will be getting the value of X. Let me help you with the answer because this is an advanced question, so you have to do into divide also. So once you solve, value of X will come out to be 0.77 volt. Into divide is your thing. I hope everybody is clear. I hope everybody is clear. Now, one more thing you have. Yes, you can metal insoluble salt, an ion electrode. Keshav, okay. Beta, soon enough. Metal insoluble salt anion electrode, that is left, but I guess we are done for the day because I'll be giving you loads of questions to practice as well. So practice those questions, and then whatever doubts you have while solving questions or whatever, after the live is done, just go to the comment section, put any and every doubt. Our team will definitely be looking into it, and accordingly we'll be planning for your remedials. But join us, join us at Lakshya JEE in English and have these sessions regularly. This is it from my side. Gaurav Singh Arora signing off. Bye bye, good night. We'll see you soon. Bye bye.